Yeah, good evening to Ananda. Good evening. Yeah, we'll start within 1 minute, right? This symmetrical components chapter we have started yesterday that we are continuing. We'll start within 1 minute. Yeah. See, yesterday we discussed about this definition of symmetrical components. Now, you see, one set of three-phase unbalanced phasors means I will say voltages. Okay, one set of three-phase unbalanced voltages. I'm going to convert into two sets of balanced phasors, three-phase. Is one I can say sequence 1, second one I will call sequence 2. Else we will call positive sequence and negative sequence. And other one is a cophasal phasor set, or else you can say zero sequence phasors. Okay. So I will say here three phase unbalanced phasors converted into two sets of three-phase balanced phasors. First one we are calling positive sequence. Three-phase balanced phasors. Phasors, right? And second one we are calling negative sequence. Three-phase balanced phasors. And next one we are calling zero sequence three-phase phasors. Zero sequence three-phase phasors. Like this. Okay. Yeah. See, I will be indicating the voltages here. Unbalanced voltages, particularly VA, VB, VC. Phase A, phase B, phase C voltages. I am following the three-phase notation as ABC. In some textbooks, the people might be giving that as RYB also. RYB, but I am following here ABC phases. Okay. Next, positive sequence means sometimes the people will take the notation as plus symbol, plus, positive, plus. Else, we will go with 1 because plus we used to take in the mathematical calculations. No. So I will be indicating this letter as 1. Indicating that letter as 1. So this positive sequence balanced voltage phasors. Voltage phasors will be like VA1, VB1, VC1. Okay. Next, negative sequence, I will take a letter 2. And zero sequence, I will take a letter 0. As a notation in the subscript, I used to give 1 for positive sequence, 2 for negative sequence, 0 for zero sequence. Okay. Now, if you write these negative sequence balanced voltages here, you will get VA2, VB2, VC2, and zero sequence voltages will come like VA0, VB0, VC0. Like this, we used to get the sequence voltages. Yeah. So see, Varun, initially we are doing only for phase analysis. The same thing you can do for the line to line also. That's your wish. Okay. Initially we are doing for phase analysis. That same thing you can extend for the line to line voltage calculation also. Yeah. One request is from Meghana. Can you please use a black background? If I use black background, I can send the notes, but you can't print it. Printable version, I can't give. If I go with white screen, then only I was capable to give the notes for you. Yeah, fine. Let's move ahead. Now, this division, how it is means, simply this phase A voltage VA, what here is equals to VA1 plus VA2 plus VA0. Okay, right. So phase A voltage in the symmetrical components can be written as positive sequence plus negative sequence plus zero sequence. Similarly, phase B voltage, you can write it as VB1 plus VB2 plus VB0. And zero sequence, you can write, phase C voltage, VC1 plus VC2 plus VC0. Like this, you can write phase A, phase B, phase C voltages in terms of the symmetrical components. Okay, done. Next, let me define what is positive sequence, what is negative sequence, what is zero sequence. That we are going to take up. Yeah, first, definition of the positive sequence components. Definition of positive sequence components. Definition of the positive sequence components. Simple. Already I said voltages positive sequence are VA1, VB1, VC1. Voltages are VA1, VB1, VC1. These are three-phase balanced voltages. You write here. Three-phase balanced voltages. What do you mean by three-phase balanced voltages here? What do you mean by three-phase balanced voltages? Magnitude of each and every voltage will be equal. Not only that, the angle between any two phasors shall be plus or minus 120 degree. Either it is plus 120 or it is minus 120. Okay, so balanced voltages in the sense magnitudes of, or better I will write mathematically, magnitudes of all the three phasors will be equal, means mod VA1 equals to mod VB1 equals to mod VC1. Okay, and phase angle between any two phasors will be plus or minus 120 degrees. Phase angle between any two phasors will be plus or minus 120 degrees. Okay. I want to tell one notation to you. All of you listen here. All of you please listen here. I want to tell one notation to you. Generally, if I write voltage V simply like this, voltage V simply in this manner V, you should think that it is having some magnitude and some angle. Rather than keeping bar all the time, VA bar, VB bar, VC bar, VA1 bar, VB1 bar, VC1 bar. Calculation wise as well as understanding wise, it is a bit difficult process, what I feel. That's why if I write simply V here, you should understand that it's a phasor. It is having some magnitude as well as some angle. If I want to write only magnitude, I will keep modulus for it. If I want to write magnitude, I will keep modulus for it. Okay. So generally this V, I will say mod V at an angle, some theta. This V is a phasor. V is a phasor. If I want to write magnitude, I will keep modulus. I will keep modulus for that voltage or current, whatever it is. Okay, let's move ahead. Let's move ahead. Next one. What is the phase sequence of these phasors? VA1, VB1, VC1. How is the phase sequence of these things? Generally, in many textbooks, what you study is positive sequence phasors will have the phase sequence same as the original system phase sequence. Same as the original system phase sequence. Yeah, let me write. Phase sequence of the positive sequence phasors. Phase sequence of the positive sequence phasor will be same as original system phase sequence. Original system phase sequence. Original system phase sequence. But generally, in the perspective of the mathematical study, I used to keep this phase sequence as ABC phase sequence. Okay. So I'll say positive sequence means it will be of ABC phase sequence. It will be of ABC phase sequence we are going to assume. Means by assuming that original system phase sequence is ABC. Okay, now I will be showing these phasors to you. VA1, VB1, VC1 phasors. I am going to show here. Okay. Just have a look here. Just have a look. See, first I am showing VA1 phasor, something like this. It is a phasor VA1. VA1 phasor. VA. Okay. Next. Remaining two phasors also I will draw. Remaining two phasors also I will draw. And we have to give names for those things. Okay. Yeah. Let's copy this phasor. And I will be showing one more phasor with a displacement of 120 degree. With a displacement of 120 degrees. I am showing that phasor. Kindly observe this. Okay. So this is another phasor. And one more phasor I am showing. One more phasor with a displacement of again 120 degree. Again 120 degree. So something like this. Okay. Yeah. So let me shrink this diagram. It's a big one we got. Yeah. So like this, we have three phasors with a displacement of 120 degree, as I said just now. Okay. Like this. See, already I indicated this phasor name as VA1. VA1. See, this angle 120 degree. This angle is also 120 degree. Not only that, magnitude of each and every phasor is equal. Magnitude of each and every phasor is equal. That's what I have shown already. In which direction these phasors are rotating? That you decide first. In which direction these phasors will be rotating? Clockwise or anti-clockwise generally? Clockwise or anti-clockwise? Yeah, anti-clockwise. Always phasors will rotate in the anti-clockwise direction. Okay, according to the phasor diagram principle, I am saying this is anti-clockwise direction of rotation. Phasors rotation. Phasors rotation. See, what do you mean by phase sequence actually? What do you mean by phase sequence? Phase sequence means it is order. It's order by which the peak values are occurring for the phase voltages or phase currents. Okay. So for example, if I get phase A voltage first at this time, if I touch the phase A voltage, next I should touch phase B voltage. Next I should touch phase C voltage to experience ABC phase sequence. To experience the ABC phase sequence, first I should touch phase A. Next I should touch B. Next I should touch C. Okay. And phasors are rotating in anti-clockwise direction. Now, if I keep this phasor as VB1 and this phasor as VC1, now if I stand at some point here, maybe at this place I am standing. At this place I am standing, right? And by standing here, I am looking at these phasors actually. I am looking at these phasors, and by looking at these phasors, you know, we have drawn this diagram as a static one. We have drawn this diagram as a static one, but you know, this diagram is continuously rotating in the anti-clockwise direction. Anti-clockwise direction with some amount of speed. Okay. Yeah. So I will show that rotation to you if possible. If possible, I am showing that rotation to you. Like this, it is rotating. So if it is rotating in this manner, first what phasor this person is seeing? VA1 he is seeing. Next, what phasor he will see? He will see VB1. Next, what phasor? VC1. Means he is looking these phasors in the order of A, B, C. By that way, this phase sequence I am going to call as ABC phase sequence. All of you getting my point? What I'm saying you, right? You should not rotate your hand. You should not rotate your hand to check what is that phase sequence. You should stand and you have to rotate the phasors. Okay, by standing here, first I will touch A1, next I will touch B1, next I will touch C1. That phase sequence we are going to name it as ABC phase sequence. Yeah. Fine. Good. Next. Next, what I will discuss is just I will try to write this VA1 equations I am saying. VA1. It's having some magnitude V1. The angle I will assume 0 degree. I am assuming that as 0 degree. How will be the value of VB1 now? How will be that VB1? Magnitude will be mod V1. Same mod V1. How is the angle? 120 degree lagging. Because after 120 degree, you will touch VB1, right? After 120 degree, you will touch VB1. So obviously, I can say this magnitude is V1 and angle will be minus 120 degree. And how is VC1? Magnitude will be same and we will touch this one at an angle of minus 240 degree. Means by an angle of 240 degree. Else VC1 leads. VC1 is in leading by 120 degree with respect to A1. That statement also you can write. Okay, so else you can write this same as V1 at an angle plus 120 degrees also. Now, if I take up this summation, VA1 plus VB1 plus VC1 summation, if you take, how much you will get? How much is this summation? Anybody please tell me? Zero. Sum of the three positive sequence voltages will be equals to 0. This is the definition of the positive sequence components. Next, we will take up the definition of negative sequence component. VA2, VB2, VC2. Those are also balanced phasors only. Let me write in the next slide. Yeah. Else I will try to write here itself. Negative sequence definition. Definition of negative sequence components. Negative sequence components definition. Already voltages notation I have given. VA2, VB2, VC2 voltages. And you know, these are three-phase balanced voltages again. Three-phase balanced phasors or voltages you can say. And you can say magnitude of this A2, B2, C2 voltages are equal. Right? Mod A2, mod B2, mod VA2, VB2, VC2 magnitudes are equal. And angle between any two phasors. Angle between any two phasors. Any two phasors will be plus or minus 120 degrees. Will be plus or minus 120 degree, we can say. Plus or minus 120 degree. And phase sequence of these phasors, negative sequence phasors, is simply opposite to that of the positive sequence. Okay? Yeah. Phase sequence. Phase sequence will be opposite to positive sequence. Opposite to positive sequence. Or opposite to positive sequence means what? What is the positive sequence phase sequence we have said? ABC, na? ABC. Reverse CBA we can write. Okay? So it will be CBA sequence. CBA sequence. And how these phasors will rotate? How these negative sequence phasors will rotate? How these negative sequence phasors will rotate? In opposite direction. Opposite direction means these will rotate in the clockwise direction. Clockwise direction. Okay. So now I will show that phasor diagram. Kindly go through it. So it is one phasor, maybe corresponding to phase A. Doesn't matter. Right? And I will show the remaining phasors with a displacement of 120 degrees. A displacement of 120 degrees. I will be showing. Yeah. 1 minute, please. So like this, we can say. This is a second phasor. And third phasor, I will be showing again with a displacement of 120 degrees. Something like this. So like this will happen. So these phasors are rotating, as we said, in clockwise direction. Clockwise direction means this will be the rotation of the phasors. This will be the rotation of the phasors. Phasors, rotation direction. Rotation direction. Okay. Now again, I should get that CBA sequence, reverse reverse phase sequence I should get. First, I will call this as VA1, sorry, VA, I'm really sorry, VA2. This I will call VB2. This I will call VC2. Same names, VA2, VB2, VC2. Same names what we have taken earlier, I have repeated. Now, as a person, if somebody is standing here and looking towards this side, then yeah. So if he is looking here towards this side, now if these phasors are rotating in what we call clockwise direction. Clockwise direction means in this direction these are rotating. And if these are rotating in this direction, first what this person will see? C phasor he will see first. After some time he will look at B phasor. After some time he will be looking at A phasor. Okay, so obviously the phase sequence will be of ACB sequence. Sorry, CBA sequence. Else you can call ACB sequence also. ACB sequence also. I'll tell you about those notation, how we can rewrite that phase sequence in a different way. Okay, but one more thing I want to tell you. One more thing. After drawing these phasor diagrams, yeah, 1 minute please. Somebody may confuse. I should show this angle 120 degree here. 120 degrees. Okay, listen here. But generally, after drawing these phasor diagrams, we might be adding one phasor diagram to other phasor diagram to get some resultant. We might be adding one phasor diagram to other phasor diagram to get the resultant. But universally, the people are following a standard that the phasors are rotating in the anti-clockwise direction. Phasors are rotating in the anti-clockwise direction. That is one notation, or that is one what we call condition the people are following. Okay, in that view, but these phasors are rotating in the clockwise direction. No, so I should make these phasors to rotate in anti-clockwise direction, but I should get the CBA sequence. I should get that CBA sequence. For that purpose, I will be interchanging these two phasors, or any two phasors I will interchange, and I will rotate them in anti-clockwise direction so that I will get that required phase sequence as CBA. Okay, yeah. So in the next slide, I'm showing same phasors I have drawn, same phasors. Now what I will do is this, instead of C2, I will keep that as B2. And instead of B2 here, I will keep this as C2. Now I will rotate these phasors in the which direction? Anti-clockwise direction only I will be rotating. So this is a direction of the phasors rotation. Phasors rotation. Again, if you want, you stand at some place here, and look at the phasors now, and these phasors are rotating in what we call anti-clockwise direction. Anti-clockwise direction. And if these are rotating in anti-clockwise direction, just observe now. Observe. First, what phasor he will touch? Phasor C he will touch. I'm starting with C. That's why I have taken C first. C. Then he will touch B phasor. Then what phasor he will touch? Definitely A phasor he is going to touch. So that is a phase sequence I can call as ACB phase sequence. Sorry, CBA phase sequence. Else, CBA, look here, CBA, like this you can write. And first three letters, I can say this phase sequence is CBA. Other than that, we can call this as BAC phase sequence also. You can call that phase sequence as BAC phase sequence also. Else you can call that as ACB phase sequence also. Any one name you can consider. Okay, yeah, I'll write here. This is CBA sequence or BAC sequence, or you can say ACB sequence. All these three will be same. All these three will be same. Similarly, you tell me the other name for positive sequence. Means ABC phase sequence we have drawn earlier. Yeah, what is that? What is the other name? Yeah, definitely Abhinandan Gupta. But generally we used to follow one notation that it will be always rotating in the anti-clockwise direction. Yeah. So for ABC phase sequence, I am saying some other names. Let's show here. ABC or BCA. That's also correct. Or you can call now CAB. CAB. All these three will be correct for the positive sequence. Okay. Now let's make a comment on this negative sequence quickly. Let's take these voltages with some notation, some magnitude and some angle. I'll write here VA2. Magnitude I am showing mod V2. Angle will be 0 degree. VB2. Magnitude V2. How is the angle of B2 with respect to A2? You tell me. How is the angle of B2 with respect to A2? Plus 120 or minus 120? How is the angle of B2 with respect to A2? Plus 120 or minus 120? Plus 120. B2 is in leading with respect to A2. Plus 120 degrees. Good, good. Plus 120 degrees. And if you take up this C2, that C2 will be in lag with respect to A2 by an angle of minus 120 degrees. By an angle of minus 120. Again, if you take this summation, that is VA2 plus VB2 plus VC2, if you take, what is the sum value we can get now? 0. That sum will be again 0. Okay, these are balanced phases. Balanced phases are opposite phase sequence as compared to positive sequence. Okay, next comment. Yeah, I will ask one simple question. In your view, you tell me. Of course, the same thing I will show while we move into the problems also. Can I say the angle of VA1 and VA2 is same? Can I say positive sequence voltage and negative sequence voltage of phase A are in phase? Because as an example or as an understanding, I consider this VA1 as mod V1 at an angle 0 degree. That's okay. And as an example or for understanding, I have shown this angle mod V2 at an angle 0 degree. That does not mean that always this VA1 and VA2 are in phase. VA1, VA2 may not be in phase. May not be in phase. Following all of you? Need not to be. Need not to be. Okay? If you want, you write that in a bracket. VA1 and VA2 need not to be in phase. Need not to be in phase. Need not to be in phase. Okay, next let's define zero sequence components or zero sequence phasors. Quickly. Zero sequence phasors or components, you can write. Phasors. Notations already we have given for this as VA0, VB0, VC0. Okay, these are not three-phase balanced phasors, and these are co-phasor phasors, as we said. These are three-phase co-phasor phasors. Co-phasor phasors, you can say. And magnitude of each and every voltage is equal. VA0 magnitude, VB0 magnitude, and VC0 magnitude. These three are equal. Not only that, phase angle between any of the two phasors is 0 degree. All are in phase. All are in phase. Right? Phase difference. Phase difference between any two phasors. Any two phasors will be 0 degrees. Will be 0 degrees. These are in phase. Okay. So next I will just show these phasors in the phasor diagram. Just I have to show VA0, VB0, VC0 in phase. Yeah, you please complete this one. I'll wait for 5 to 10 seconds. Please complete it. Sir, magnitudes of positive and negative sequence components equal. Need not to be. Need not to be. They may be equal, may not be equal. We don't know. Need not to be. Sir, VA1 and VA2 angle is 0, sir. It's in phase. Deepa, that's what I am saying you. That's why I have explained till now. I assumed that angle is 0 degree, but VA1, VA2 need not to be in phase. Need not to be having equal angle. Need not to be having 0 degrees angle. Okay, done. So now I will be showing this zero sequence phasor. Yeah. So just I will be taking up phasor something like this. This itself I used to call VA not voltage, VA not voltage, and same phasor I will repeat. Same phasor I will repeat with a name VB not, and I will repeat the same phasor with a name VC not also. Right? So this is a VB not phasor, and that is VC not phasor. All the three are of equal magnitudes and moreover in phase. But strictly speaking, you no need to draw three phasors, something like that. No need to draw the three phasors, something like that. What you should show is only one phasor you should draw. That itself you should call as VA not, VB not, VC not. Okay? Yeah. Else, the even better way of representing this is in this manner. So this itself is a phasor VA naught or VB naught or VC naught. Not only magnitudes, angles also equal. Angles also equal. See, if you want to write this, let VA naught is some magnitude V naught at some angle 0 degree. VB naught is some magnitude V naught at an angle 0 degree. VC naught will be again same mod V naught at an angle 0 degree. Like this you can write. Again, same comment. It's not necessary to say zero sequence voltage will have an angle of 0 degree. It's not necessary to say zero sequence voltage will have an angle of 0 degrees. Okay, it may be a different angle, but I said here, let's assume like that. If that's the case, what is summation of VA naught, VB naught, and VC naught? How much is this? All three are equal, so it will come to be 3 times of zero sequence voltage. Come to be 3 times of the zero sequence voltage. 3 times of zero sequence voltage. Yeah, dear anonymous attendee, have you checked the student portal? Have you checked the student portal? I myself uploaded the notes today morning. Then again you are asking me notes is not uploaded. I have uploaded the notes in the student portal. Please check once. Yeah, listen to me, listen. How will be the rotation of these phasors, means zero sequence components? Whether these zero sequence voltages will rotate or static? Anybody? Whether these zero sequence voltages are rotating or stationary? Anybody? 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 Am I visible on the screen? Am I visible on the screen? Ah, yes. Yeah, please check yourself, Mr. Prasad. Saumitri Prasad, please check yourself. Please check your settings. I am visible on the screen. Yeah. These are not stationary. Dear students, these are not stationary. Already we are saying these are phasors, right? What do you mean by phasor? Having a magnitude as well as having some angle, and these are rotating vectors. So zero sequence phasors will also rotate in the anti-clockwise direction. Okay, these are rotating in anti-clockwise direction. Rotates in anti-clockwise direction. ACW. These are phasors. Okay. Yeah. Next thing. Let's make some sort of conclusion with respect to this voltage and all. Let's take up like this. We have written the voltages earlier, right? Let me copy them. This one. Set of voltages we have written already. I'm copying that set of voltages converted into symmetrical components. Yeah, just have a look here once. Have a look here. See, VA, VB, VC, actual ABC voltage. VA, VB, VC, unbalanced, of course, whatever. These are having a frequency of F. Frequency of these phase A, phase B, phase C voltages is F. Frequency of those phasors is F. What will be the frequency of the positive sequence phasors? what will be the frequency of the positive sequence phases? It will be remain same, F1. Remain same, F1. Okay. See, what will be the frequency of these negative sequence phasors? These are rotating in opposite direction, but still, I will say the frequency as F only. I will say the frequency as F, fundamental frequency only. What will be the frequency of the zero sequence phasors? What will be the frequency of the zero sequence phasors? These are not static. These are also rotating. These are also having a frequency of F. Not 3 times of fundamental frequency. Not 3 times of the fundamental frequency. It is not Fourier series analysis what we are doing. It's not Fourier series analysis we are doing. It's a symmetrical component study. Symmetrical component study. So the frequency of these zero sequence phasors will be remain same F. In the sense, if the actual ABC components are having a frequency of 50 Hertz, positive sequence voltage frequency 50 Hertz, negative sequence voltage frequency 50 Hertz, zero sequence voltage frequency also 50 Hertz. This we should remember. Yeah, now I'm asking one simple question to you. What is summation of these ABC voltages? What will be the summation of A, B, C voltages? How much is that? Anybody? What is summation of A, B, C voltages? Is it 0 or non-zero? See, VA1 plus VB1 plus VC1, 0. Sum of the 3 means you should sum all 9 numbers, right? All these 9 numbers you have to add up. That's it. VA2 plus VB2 plus VC2 also 0. But you know, VA0 plus VB0 plus VC0, that will come to be 3 times of the zero sequence voltage. 3 times of zero sequence voltage. Okay? 3 times of the zero sequence voltage. Getting me? 3 times of zero sequence voltage. Which voltage is VA, VB? What's the doubt? I don't know. Next thing. Next thing, I'm asking one very simple question to you. Simple question. Very small question it is. Maybe it's an objective question, you can say. Objective question. Just look here. If VA plus VB plus VC equals to 0 in a three-phase system, then which of the following statements are correct? Correct. So it's a MSQ question, multiple select question. MSQ, multiple select question. Option A, zero sequence voltage of all 3 phases is 0. Is 0. B, system is balanced. System is balanced. C, system is unbalanced. Unbalanced. D, system may or may not be balanced. May not be balanced. Yeah. System is surely balanced. Surely balanced. System is surely unbalanced. System may or may not be balanced. Zero sequence voltage of all the 3 phases is 0. Which statement is correct? Which statement? Statement or statements, whatever it is. Which one? Anybody please tell me? First of all, already we have some idea just now as we studied. Sum of the three voltages equals to 3 times of zero sequence voltage, and he said that is equals to 0. 3 times of VA0 is equals to 0 means VA0 will be definitely equals to 0. So I can say zero sequence voltage of all the three phases will be 0. See, if the zero sequence voltage of phase A is 0, phase B and phase C, zero sequence voltage is also 0. That's one statement. A is perfectly correct. A is perfectly correct. What about balanced or unbalanced? What about balanced or unbalanced? How we can sure whether the system is balanced or unbalanced? See, one thing, please listen here. So I'm saying in the solution first, as VA plus VB plus VC equals to 0, that's what I said just now. 3 into VA0 is equals to 0. That implies VA0 is equals to 0. So A is correct. Option A is correct. Now we should check about remaining. See, listen. Some people might be in an impression that if sum of the three voltages equals to 0, the system is balanced. It may not be. It may not be balanced. How I can say the system is balanced is magnitudes of the three voltages are equal. Phase angle between any two voltages is 120 degrees. Then only we can say that the system is balanced. Else, we can't say that the system is unbalanced. Else, I can say in this manner. If the system is balanced, listen please, listen my words. If the system is balanced, then VA plus VB plus VC equals to 0. But if VA plus VB plus VC equals to 0, the system need not to be balanced. So that VA plus VB plus VC equals to 0, it's a necessary condition, necessary to say the system is balanced, but it is not sufficient. It's not sufficient. Okay, so you're right. For balanced system, magnitudes of all voltages will be equal. Magnitudes of three voltages equal. Three voltages will be equal. And phase angle will be phase angle between any two voltages. Any two voltages or voltage phasors will be plus or minus 120 degree. This is a condition to say that the system is balanced. If VA plus VB plus VC equals to 0, it is not sure to say that the system is balanced. The system may be balanced, may not be balanced. Okay, yeah. So if VA plus VB plus VC equals to 0, system may or may not be balanced. May or may not be balanced. May not be balanced. So our option D is also correct. So I can say A and D are correct, right? D is also correct. D is also correct. So A and D options are correct. Yeah. So I will show that Manikanta in the doubt session. Please remind me that to draw in the doubt session. Okay, let's continue. I'm taking up one small example here. Some example. Kindly understand. Look. First, I am taking positive sequence phasors, voltages. Positive sequence phasor voltage I am taking, right? Positive sequence phasors. Let me draw. So this is phase A. Else, I'll show like this. For easiness in the understanding and calculation, I'm doing like this. Phase A, voltage. Yeah. Phase A voltage means you can call it is VA1. VA1. And how is VB1 to you? VB1 will be 120 degree lagging with respect to this. VB1 will be 120 degree lagging. 1 minute, please. So VB1 will be 120-degree lagging. So I'll show that. Look at this. It's 120-degree lagging I'm showing here, like this. This is VB1 voltage, VB1. Next, VC1 voltage. VC1 voltage, I will be showing at an angle of 120-degree again. 20-degree, something like this, you can say. Yeah, so this is VB1 voltage, and this is VC1 voltage. VC1 voltage. These are positive sequence voltages. Positive sequence voltages. Now I am going to show negative sequence voltage here. I'm going to show the negative sequence voltages. So I will show here negative sequence voltages. But here for easiness in understanding, I am assuming that VA2 is in phase with what we call VA1. VA2 is in phase with VA1. That's the assumption I am making. That's the assumption I am making. Yeah. So I am showing here. These are the three voltages. This voltage I am naming as VA2, but this will come to be VC2, right? And this will come to be VB2. This is rotating in anticlockwise. This is also rotating in anticlockwise direction. Now, the question is, you have to add these two phasors together. Means positive sequence phasors and negative sequence phasors, you have to add together in order to get the resultant phase A and phase B voltages. Resultant phase A and phase B voltages. Okay. So that you have to do in the manner of a phasor diagram addition. Phasor diagram addition. See, both are rotating in anticlockwise direction. But first will be of ABC sequence. Next, maybe of ACB sequence. Whatever it is, doesn't matter. You have to add VA1, VA2 together, VB1, VB2 together, VC1, VC2 together. That addition you have to make. Okay? Yeah. Anybody? Please do that. Please do that. Please try to do that. I'm copying this positive sequence set of voltages first. Positive sequence set of voltages I am copying to the next slide to make that addition. This will be the positive sequence set of voltages. Next, negative sequence set of voltages I am copying. Negative sequence set of voltages I am copying. Right? Now, we have to superimpose the positive and negative sequence voltage phasors together like this. Means negative sequence phasor diagram, we have to superimpose on the positive sequence phasor diagram. By making that what we call addition, let me show that VA2, VB2, VC2 in blue color. I'll say it is VA2 phasor. It will like this. VA2 phasor is this one. And this is VC2 phasor. Okay. And this is VB2 phasor. Like this, we'll have the phasors. VA2. Blue color I am showing just to have some difference. VC2. And this phasor is VB2. Blue color phasor. VB2. VB2. Now, add VA1, VA2 together. By adding that, VA1, VA2 are in phase only. Resultant voltage will rise up in the same direction. Resultant voltage will rise up in the same direction. So, summation of that VA1, VA2, I'm doing that in the red color. So, this may be that resultant. Okay, so this is VA1 plus VA2. VA1 plus VA2. Next thing. Again, see, you should add B phasors together, C phasors together. We should not add one B phasor with the other C phasor. That addition we should not make here. I have to get VB1 plus VB2 now. VB1 plus VB2. Kindly look. This is VB1, black color. Blue color, VB2. Now we have to add these two. So addition of these two means by means of the parallelogram principle. Parallelogram principle, you can say. Yeah. So this is a C2 phasor I am drawing. Parallelogram principle. Right? Like this you can say. And I have to draw B2 phasor also. Okay. So like this you may get. Like this you may get. And you will get somewhere resultant. Yeah. So like this almost approximately you can take this one. So this may be the summation of, okay. Sorry, this. B1, no, B1 we have to add. B1. Let me extend this a little bit more. Okay. So B1 we have to add now. This is B1 phasor. So after adding that B1 with B2, B1 with B2, we will get the resultant phasor in the red color, something like this. We'll get VB1 plus VB2. VB1 plus VB2. Next again, you should take VC1 plus VC2 here. VC1 plus VC2. We have VC1 and this is VC2. Now you add these two by parallelogram principle again. Parallelogram principle like this. Okay. And this is another phasor. You can get something like this. And you can get that resultant here. You can get that resultant here. Like this, you can get that resultant. And this will come as a VC1 plus VC2. VC1 plus VC2. Okay. Now, just you have to make one observation that how will be this VA1 plus VA2, VB1 plus VB2, VC1 plus VC2? How will be these three phasors to be? Whether these three phasors are balanced or unbalanced? Balanced phasors or unbalanced phasors? Just think about it. We will make some conclusion, right? So just 1 minute, please. I'll come back 1 minute. See, the resultant voltages are becoming unbalanced. That's perfect, right? So you write that statement if you want. Resultant voltages are unbalanced. Voltages are unbalanced. Why? Why these are becoming unbalanced means very simple reason. Simple reason is that VA1 plus VA2 phase A voltage, what you are saying now, that is of larger magnitude compared to B and C phases. That's it. That's sufficient to say that the system is unbalanced. Okay, the voltages are unbalanced. Okay, I'm asking one simple question to you. How is a positive sequence voltage here? How will be these positive sequence voltages? Whether these are balanced or unbalanced? Positive sequence voltages. Balanced or unbalanced? Balanced. These are positive sequence balanced. How are these negative sequence voltages? Also balanced. See, positive sequence set balanced, negative sequence set balanced, but if we are adding these two, we are getting the resultant as unbalanced. So what comment you have to make now is, if the system is unbalanced, definitely it will consist both positive sequence and negative sequence components. Else, a set of unbalanced phasors, something like this, can be converted into two sets of balanced phasors. One is of positive sequence, other one is of negative sequence. This is a statement the Fortescue professor has given. We have studied that in a reverse way. First I taken positive sequence, then negative sequence, we added both, we got unbalanced. Reverse statement is what? Unbalanced phasors can be converted into a set of positive sequence and negative sequence phasors. Following all of you, right? So from this, the conclusion, what we can write here is, a set of unbalanced phasors, that implies a set of unbalanced phasors can be converted into two sets of balanced phasors. I'm talking the statement only in the way of view of three-phase system. Okay, two sets of balanced phasors of different phase sequences. Different phase sequences. Okay, different phase sequences. Why positive sequence is more than negative sequence? That's a general scenario we have taken. If you want to take negative sequence as more compared to positive sequence, no issue with that. Okay, see, but still, after converting one set of unbalanced phasors into two sets of balanced phasors, still if some value is left in the phase A voltage or phase B voltage and phase C voltage, that whatever the value left in the phase A, phase B, phase C voltages, we are going to name it as zero sequence component. Okay, right. I'm writing that statement here itself. Even after doing conversion, if still any value left in the phase voltages, any value left in the phase voltages, it will be called as yeah, it will be called as zero sequence phase voltage, will be called as zero sequence. Okay. Right. So next, in the very next step, what we'll do is simply, I'll take one set of unbalanced phasors. I will redraw that into positive sequence, negative sequence, and zero sequence as we are discussing till now. Okay. So by that point, we are going to introduce some more terms to you in the analysis. Okay. Yeah. So let's take here set of unbalanced phasors, something like this. So it doesn't matter what is that magnitude and what is that angle. Okay, that's a phase A voltage, and I have something like this, a phase B voltage. And these two magnitudes may not be equal and not having an angle of 120 degrees. And this is some phase C voltage, like this. Okay, so this is phase C voltage, and you write this is a three-phase unbalanced phasor set. Unbalanced voltage phasors. These are rotating in anti-clockwise direction, and this is going to be transformed. This phasor diagram is going to be transformed into first positive sequence I am showing. Okay, else I'll show like this. That's your wish. This is a phase A voltage in the positive sequence, and I will show phase B voltage in the positive sequence here. Phase B voltage in the positive sequence. Okay. So you can get something like this. It's a phase B voltage in the positive sequence and phase C voltage in the positive sequence. Phase C voltage in the positive sequence. We may get something like this. These are balanced already, we said. It is a voltage VA1 and this is VB1 and this voltage is VC1. Okay, and this angle is 120 degree positive sequence. It's also 120 degree. And negative sequence I am showing plus this phasors plus negative sequence I am showing. So like this. So this is a phasor VA2. And these two phasors you should check now. And this will come to be VC2 phasor. And this will come to be VB2 phasor. That's how we have to give the names for these phasors according to their rotation and phase sequence. 120 degree is that phase angle. So first we'll touch A, next C, next B. This plus, this plus. I have zero sequence, only one what phasor I will draw, else 3, no issue. This is a VA0 phasor. Don't bother about these numbers, these magnitudes and all. These are not to scale. Not to scale. These are some approximations I am taking. So it's a VB0 phasor and it's a VC0 phasor. VB0 phasor and VC0 phasor, and these phasors also rotating in the anti-clockwise direction. So by adding these three phasor diagrams together, we used to get this unbalanced phasors set. Okay, so this is positive sequence, three-phase phasors, and this is negative sequence, three-phase phasors, and this will be of zero sequence, three-phase phasors. Zero sequence, three-phase phasors. Left phase voltage means, for example, if you have VA some number, you are dividing that into positive and negative sequences. But still, if some number is left, from the phase A voltage, that is going to be called as zero sequence. Sir, positive and negative sequence magnitudes are equal. Need not to be. Sivaramakrishna. Sivaramakrishna, positive and negative sequence magnitudes need not to be equal. Unequal also may happen, equal also may happen sometimes. So negative sequence should be rotated clockwise direction only. Shivanath, it should be rotated in clockwise, but according to our convenience, we converted that into anti-clockwise by changing the phasor names. By changing the phasor names, we converted that into anti-clockwise. So positive other than 0 degree is possible for 0 sequence. Yes, it may not be 0 degree. 0 sequence voltage angle need not be 0 degree. Okay, see, actually, listen here. I'm introducing some more thing to you. Just listen. VA1 we have, right? VA1. If I shift VA1 by an angle of 120 degree in the anti-clockwise direction, I will get VC1. I'll get VC1. Means simply VA1 shifted by an angle of 120 degree will give VC1. VA1 shifted by an angle of 240 degree will give VB1. Means it may be possible, listen my words, it may be possible to replace VC1 in terms of VA1 with a phase shift of 120 degree. It may be possible to replace VB1 in terms of VA1 with a phase shift of 240 degree in the anti-clockwise direction. Similarly, VB2 we can replace in terms of VA2 with a phase shift of 120 degree. VC2 we can replace in terms of VA2 with a phase shift of 240 degree. And already you know VB0 and VC0 values are nothing but VA. So simply what my interest is to tell you, total 9 symmetrical components here. VA1, VB1, VC1, 3. VB2, VC2, VA2, 3. And VA0, VB0, VC0, 3. Total 9 symmetrical components here. These 9 symmetrical components I want to convert into 3. Means I want to rewrite phase B and phase C symmetrical components in terms of phase A. In terms of phase A. For that purpose, I am introducing one phase shift operator. Phase shift operator. Okay. So the next heading, what I am going to take here is phase shift operator. I will come back to this diagram after discussing the phase shift operator. Okay. Yeah. So the next heading here is phase shift operator. See, different notations the people will follow for this one. Some people will use a letter A, some people will use a letter K, some people will use alpha, like that. Various notations are there, but I will be going with alpha. I will be going with alpha on my own notation. Okay, right. Yeah. Alpha is a phase shift operator. It introduces, see this one. It introduces 120 degree phase shift in anti-clockwise direction. Anti-clockwise direction. 120 degree phase shift in the anti-clockwise direction without changing the magnitude of the phasor. Without changing the phasor magnitude. Phasor magnitude. Without changing the phasor magnitude. Means the magnitude of alpha should be equals to 1. It should not change the magnitude of the phasor which you are going to shift. So magnitude of alpha should be equals to 1. The angle will be 120 degree, which you need to make. So therefore, alpha is going to be written as 1 magnitude at an angle of 120 degree. Like you know J in the complex numbers or I in the complex numbers. J or I in the complex numbers, right? The J will give a shift of 90 degree in the anti-clockwise direction. Magnitude of J equals to 1. In the similar way, we are introducing other phase shift operator in the 3-phase system analysis. Okay, what's the use of this phase shift operator? What's the use of this phase shift operator? By this alpha, by this phase shift operator alpha, it is possible to convert phase B and C B and C, symmetrical components into phase A. By this, the total number of symmetrical components in the analysis will be reduced to 3. That implies number of symmetrical components will be reduced to 3. So that analysis will be simple. Okay, so before going with this alpha, modifying the phase B and phase C voltages, I want to do some sort of exercise with this alpha. Okay, alpha equals to 1 at an angle 120. I will write that in different ways. Alpha in different ways. Alpha is equals to 1 at an angle 120 degrees. Okay, can you tell me what is this in rectangular form? It's in polar form actually. It's in rectangular form if you like. Cos 120 degree plus j sin 120 degree. Cos 120 degree plus j sin 120 degree. What is cos 120? I think it's minus 0.5 plus j sin 120, that will be 0.866. J 0.866 means this number you can write minus 1 by 2 plus j root 3 by 2. Different ways of writing this one. Minus 1 by 2 plus j root 3 by 2. J root 3 by 2. Okay, now I will take this alpha in some other way. Alpha equals to 1 at an angle 120. I can write that as 1 into e power j 2 pi by 3 by using Euler's theorem. R into e power j theta, nothing but r at an angle theta. So 1 at an angle 120 is r at an angle theta. That we can write as r into e power j theta. R is 1 into e power j 2 pi by 3. Like that we can write. Okay, now what is alpha square value? Alpha square means you have to say 1 at an angle 120 degree whole square. 1 at an angle 120 degree whole square. Else you can say 1 into e power j 2 pi by 3 whole square. Whole square means 1 square, 1. E power j 2 pi by 3 whole square means multiplied with 2. Means angle will become double. In this squaring, magnitude will be squaring. The angle will become double. So this magnitude will be 1 square in the sense 1 only, but angle is 120 degree into 2. So it will come 1 at an angle 240 degrees. That's the alpha square. What is alpha cube value? 1 at an angle 120 degree whole cube. 1 cube, 1. The angle 120 into 3. What is that 120 into 3? That is 360 degrees. Nothing but 1 at an angle 0 degree. 360 degree? 360 degree rotation means we have reached to the original place where we have started. So how much angle we have covered? 0 degree. Okay, sometimes this 1 at an angle 240 degree can also be written as 1 at an angle minus 120 degree also. 1 at an angle minus 120 degree also you can write. See, what is alpha conjugate here? What is alpha conjugate? Tell me please. Alpha conjugate is nothing but 1 at an angle 120 degree whole conjugate. Conjugate in the sense magnitude will be remain same. What will happen to angle? Negative sign. Already we have positive symbol. So minus 120 degrees you are going to get. That 1 at an angle 120 degree is nothing but alpha square. So the value of alpha conjugate is nothing but alpha square. Alpha square. Right? Next thing. What is this number? I'm writing this value. Alpha power 79. How much? Alpha power 79. Actually, alpha cube equals to 1, right? Alpha cube is equals to 1. So you try to write this 79 with the multiplication of 3. So that alpha cube you can replace with 1 and remaining number you can write. First of all, 79 you have. Is it divisible with 3? 79. Is it divisible with 3? Yes. 9 plus 7. No. 9 plus 7 means it is 16. It's not divisible with 3. So I will rewrite this as alpha power 78. Is it possible? Yeah. Into alpha. You check this one. Alpha power 78 means I can write alpha cube whole power 2, 6, 26. You have into alpha. Alpha cube whole power 26 into alpha. See, 3 into 26 if you take. 3 into 26 you get 78. And alpha cube is 1. So it will be 1 power 26, 1. So this is nothing but alpha. This is nothing but alpha. That alpha value was 1 at an angle 120 degrees. That's the value of alpha power 79. Alpha power 79. Okay? Yeah. Next, one more number I am taking. Alpha power 1000. How much? How much is this value? Alpha power 1000? Alpha power 1000. 1000 is not divisible with 3. We have to rewrite that as a divisible with 3. So I can write this one alpha power 999 plus 1. Okay, so this is nothing but alpha power 999 into alpha. Alpha power 999 is nothing but alpha cube whole power 333. Alpha cube is 1. 1 power 333 will give 1 only. It will come as alpha. Come to be alpha. Okay, next one. Next. So I want to take one more simple calculation here. 1 plus alpha square, how much? 1 plus alpha square, how much? Anybody? 1. Okay. Alpha. 1 at an angle 120 degree. Alpha square. 1 at an angle 240, or you can write 1 at an angle minus 120. That will be equals to 0. 1 plus alpha square is equals to 0. Okay, done. Next one. Next one. What is this value? Alpha plus alpha square minus 1. How much is this number? Alpha plus alpha square minus 1. Anybody? See, already you have written 1 plus alpha square equals 0 now. Then what is alpha plus alpha square? Minus 1. Alpha plus alpha square is minus 1. And you have already minus 1 here. So this number will be minus 2. Or else 2 at an angle of 180 degrees per unit. 2 at an angle of 180 degree per unit. Like that also you can write that minus 2. Minus 2. Else you write the same as 2 at an angle minus 180 degree also. That's also correct. Minus 180 degrees. Okay. Next one. Next one I am asking you. What is this alpha minus alpha square value? Alpha minus alpha square value. See, actually, calculation of this alpha minus alpha square you can do in 2 methods. Particularly as you need to use a virtual calculator in the exam. Virtual calculator in the exam, you can do this in 2 ways. One way, alpha you keep in rectangular form. Alpha square also you keep in rectangular form. Take up that value, you get the answer. That's one method. The other method is going with phasor diagram analysis. Going with the phasor diagram analysis. Yeah. So for example, if you take up the phasor diagram analysis here, simply I will show. This is 1 at an angle 0 degree now. So this is 1. And 1 at an angle 120 means alpha. Alpha it will be shifted by an angle of 120 degree in clockwise. Sorry, anti-clockwise. So alpha I am showing here. Alpha I am showing. It has to be shifted by an angle of 120 degree in the anti-clockwise. In the anti-clockwise, it has to be shifted by an angle of 120 degrees. So like this you can say, this is alpha. This is alpha. 2 techniques are there. One, going with the phasor diagram. Next one, substitute the rectangular value. Rectangular value for alpha and alpha square. Calculate that. Next one, alpha square. I will show. Alpha square, it will be shifted by an angle of 120 degree. So like this, you may get that alpha square. You may get this alpha square. Now, what you have to calculate? Alpha minus alpha square, we need them. Alpha minus alpha square. So first you take minus alpha square value, right? And then you have to add that alpha and alpha square together. I think space may not be sufficient. Let me reduce this size. Yeah, say this. Alpha minus alpha square, na? So minus alpha square, I should take in opposite direction to this one. Minus alpha square, I should take in opposite direction to this. Maybe like this you can take. This is minus alpha square phasor. And then you take that alpha minus alpha square summation. Alpha minus alpha square summation. So this is the parallelogram principle of addition I am making. Parallelogram principle of addition. It may come almost a mistake, I think. Redraw. I get this alpha phasor, something like this. Okay. Now, if you add these two together, you may get the resultant phasor something like this. So this will come almost with an angle of 90 degree. That's what my intention to tell you. This angle will come almost equals to 90 degree here. And this phasor is nothing but alpha minus alpha square. Alpha minus alpha square. And this angle will be 90 degrees. And what is this magnitude? Magnitude will be √3 times. √3 times angle is plus 90 degree. It will be shifted by an angle of 90 degree in the anti-clockwise direction. Else you write this one as j times √3. And write it as j times √3. Getting? Next, what is the okay? This is √3 at an angle plus 90 degrees. What is this? Alpha square minus alpha. Alpha square minus alpha, if you do, this is already alpha square minus alpha. You should draw it down. Should draw this one down. And if you add these two, you will get exactly opposite phasor with an angle of 90 degree lagging. Means if you calculate this alpha square minus alpha, you get this as √3 at an angle minus 90 degree, or you can call minus j √3. √3 at an angle minus 90 degree, or you can say that as, yeah, how √3? Dinesh, we have to go that with what we call parallelogram principle from your intermediate parallelogram principle. If you have a doubt, you ask me at the in the doubt session. How 180 degree? Minus is nothing but 180 degree only, right? Rokana Satish, you write this -2 as a what we call polar form. Polar form is magnitude will be 2. What's the angle? Angle of -1. That is nothing but 180 degree shift. 180 degree shift. Anyhow, still if you have a doubt, you can comment it on in the doubt session. Next thing. I want to take up this one more simple calculation, that is, what is 1 minus alpha? How much? Else you take 1 minus alpha square, how much? 1 minus alpha square. 1 you have, minus alpha square you have. Just you have to add these two together. After adding these two, the magnitude will come √3. By using again parallelogram principle, you have to do that addition. By using parallelogram principle, this is alpha, sorry, this is minus alpha square, and this is 1. You should add these two, something like this. And finally, you are going to get this 1 minus alpha square here. Is 1 minus alpha square. And this magnitude will be again √3. Again, by means of the parallelogram principle also. And this angle, look here. This angle will be 30 degrees. Will be 30 degrees. How in the sense? Just listen to me. Just listen to me once. I am going to tell these angles to you a bit quickly. Angle between 1 and alpha, that is 120. Angle between 1 and alpha is 120 degrees. What is the angle between 1 and minus alpha square? The angle between 1 and minus alpha square means this angle, how much? 60 degrees. That will be 60. And obviously, this angle will come to be 30 degrees. It will cut that angle exactly into half. 1 minus alpha square cuts this angle exactly into half. So it will be 30 degrees. And 1 and minus alpha square angle will be 60. And this angle will be 120 degrees. Clear? So 1 minus alpha square, magnitude will be √3, angle will be plus 30 degree. It will be in leading. It will be in leading with respect to 1. So √3 at an angle of plus 30 degree, you can see. And what is 1 minus alpha? Anybody please tell me? How is 1 minus alpha? Alpha you have here. Minus alpha means it will come down like this. Minus alpha means it may come something like this. And if you add that 1 and minus alpha together, you may get the phasor something like this. And again, this magnitude will be √3. Angle will be minus 30 degree. Minus 30 degree. It will be lagging. So it will be √3 at an angle of minus 30 degrees. √3 at an angle of minus 30 degrees. Okay. Right. Next, let's move to the what we call phasors. Unbalanced set to positive sequence, negative sequence, and zero sequence. I will be using alpha there. Yeah. This is a slide at which we have started that alpha. Simple, very simple thing. VA1 you have here, VA1. You multiply this VA1 with alpha. Multiply this VA1 with alpha means VA1 phasor is shifted by an angle of 120 degree in the anti-clockwise direction without changing the magnitude. Means alpha into VA1 if you do, that will go on to VC1. Means it will be superimposing to VC1. So VC1 you replace with alpha into VA1. VC1 you replace with alpha into VA1. Okay, now VC1, if you multiply with alpha, VC1 if you multiply with alpha, then it will be shifted by an angle of 120 degree in the anti-clockwise direction. So it will be superimposing onto VB1 obviously. So VB1 equals to alpha into VC1. VB1 is nothing but alpha into VC1. Already you said VC1 is alpha into VA1. So it will be resulting into alpha square VA1. Alpha square VA1. Clear? Next one. VA2 we have, right? VA2. Multiply this VA2 with alpha. Multiply VA2 with alpha. That will be superimposed onto B2. Means VB2 you replace with alpha into VA2. Again, VB2 multiplied with alpha will give VC2. So VC2 is nothing but alpha into VB2. VB2 multiplied with alpha will give VC2. So VC2 equals to alpha into VB2. That is nothing but alpha square VA2. Alpha square into VA2. And already you know VA0, VB0, VC0. All these three are equal. VA0, VB0, VC0. All these three are equal. Kitna? Calculate it. Why you are asking me? Alpha square minus 1. I've given. I think sufficient basic. You calculate it on your own way. Kitna? Alpha square minus 1. Draw the phasor diagram. Take minus 1. 1 alpha square. Na? Take minus 1. Okay? Minus 1. Alpha square. Alpha square minus 1. If you add, you get 150 degree lagging angle. So it will be √3 at an angle minus 150 degree. Alpha square minus 1 will be √3 at an angle minus 150 degree. Kirtana? Draw in the phasor diagram. Sir, we can superimpose on any phasor. What is that question you are asking, Vamshi? How you write VC1? Multiplying this VA1 with alpha. Multiplying VA1 with alpha means VA1 phasor will be shifted by an angle of 120 degree in the anti-clockwise direction. So if it is shifted by an angle of 120 degree in the anti-clockwise direction, it will be superimposed onto C1. Means that VC1 is nothing but alpha times of VA1. Similarly, VC1 multiplied with alpha will give VB1. Means VB1 is nothing but alpha times of VC1. Already VC1, you know, alpha into VA1. So alpha into VA1, alpha square VA1 we have to write. Alpha square VA1 we have to write. Clear? So the positive has to be in phase. Again, you are asking the same question, Shiva. I said you many times, positive and negative sequence components may or may not be in phase. May or may not be in phase. Why you are asking the same question again and again? Okay. Let's move with the voltages VA, VB, VC here. What do you mean by phase A voltage generally? In terms of symmetrical components, zero sequence voltage plus positive sequence voltage plus negative sequence voltage. VA equals to VA0 plus VA1 plus VA2. That's it. And what is VB? Phase B voltage, VB0 plus VB1 plus VB2. Phase B. If you want, I will display those equations to you. This one. VA equals to VA1 plus VA2 plus VA0. VB equals to VB1 plus VB2 plus VB0. Similarly, VC also. Those equations I am repeating. But now, I want to write these B symmetrical components in terms of A. B symmetrical components in terms of A. Okay. So, I will be taking this VB0 equal to VA0. VB0 is nothing but VA0 here. Plus, what is VB1? Just now in the phasor diagram we can get. Look in the phasor diagram and write. VB1 is what? Alpha square VA1. VB1 is alpha square VA1. Okay. What is VB2? What is VB2? VB2 alpha into VA2. VB2 is alpha into VA2. This is one equation. This is one equation. Phase B voltage in terms of phase A symmetrical components. Next one. What is VC? VC0 plus VC1 plus VC2. Okay. What is VC0? Nothing but VA0. What is VC1? What is VC1 here? VC1 is alpha into VA1. VC1 is alpha into VA1. If you look at VC2, you get that as alpha square into VA2. Alpha square into VA2. Clear? So this is another set of equation. So all the three phase voltages we got in terms of phase A symmetrical components only. Okay, you call if you want. This is equation 1, and this is equation 2, and this is equation 3. You try to write these three equations in the matrix form. The matrix form. Bhavani, that's what we are discussing till now, right? What's the use of this alpha phase shift? What's the use of this phase shift? To convert phase B, phase C symmetrical components in terms of phase A. That phase shift will act as a multiplication factor. Multiplication factor to the phase A components to get phase B and phase C components. Okay, so by writing these three in matrix form, left side matrix I will call VA, VB, VC. Left side matrix I am calling as VA, VB, VC matrix. Right? So VA, VB, VC is equals to what you will get now? You will get one big matrix here, maybe of 3 by 3 size matrix we are going to get here. 3 by 3 size matrix you will get, and that multiplied with VA0, VB, VA0, VA1, VA2. Right? So I am showing here first VA0, VA1, VA2, VA1, VA0, VA1, VA2. And what are the coefficients here? In the phase A voltage, it is 1, 1, 1. Coefficients are 1, 1, 1. Phase B equation coefficients are 1 alpha square alpha. 1 alpha square alpha. And here it is 1 alpha alpha square event. 1 alpha alpha square event. Okay. Like this, you can write it matrix notation. And this VA, VB, VC vector, or you can say matrix, whatever it is, as shortly VA, VC. It's a column vector. You have to remember this. It's a column vector. And this VA0, VA1, VA2, it's also a column vector, but I will call that one as V012. 012, symmetrical components, calling that as V012. Generally in the exam, all of you listen to me. Yes, Dinesh. Listen here. Where they are used mathematically, we are discussing Bhavani. You ask me if you have any doubt in doubt session, elaborate your doubt. Okay, listen here. Generally, sometimes in the exam, just they will say sequence voltages or symmetrical components of voltages. Both will be same name. Symmetrical components of voltages or sequence voltages, simply like V0, V1, V2. Simply they will say V0 some number, V1 some number, V2 some number. They didn't mention for what phase these sequence voltages belongs to. Whether these are phase A sequence voltages, phase B sequence voltages, phase C sequence voltages, they may not mention sometimes. If they have not mentioned, blindly, you have to assume that these are phase A sequence voltages only. So, as far as a notation is concerned, I'll call this VA0 as V0. I'll call this VA1 as V1. I'll call this VA2 as V2. Like this, we are going to call. And whatever the relationship we have between this VA, VC and V012, this matrix I am going to call as symmetrical component matrix. I will name it as capital A. Okay. So this is symmetrical component matrix. We are naming this as A. Matrix A. So from this, you can write column vector VA, VC is equals to matrix A into V012. Matrix A into V012. Like that you can write. Same equations we can follow. Same equation we can follow even for currents also. Just by changing the name V as I. Okay. Next, for example, if you take A inverse multiplication on both sides, you get A inverse into VABC equal to A inverse into A into V01. A inverse into A is identity matrix. So, what will happen to the symmetrical components of voltages now? Symmetrical components of voltages will be A inverse into VABC. A inverse into VABC. Like this you can see. Now let me expand it. V012 equals to A inverse into VABC. I am going to expand that matrix. Okay, let's move to the next slide to write that expanded matrix. V012 is nothing but VA0, VA1, VA2 here. V012. Nothing but VA0, VA1, VA2 equal to. First I will write A inverse matrix. That A inverse matrix will come like 1/3. We have to do that inverse with the help of that linear algebra. So after doing inverse, you will get that matrix as A inverse equals to 1/3, 1, 1, 1, 1 alpha square, you get 1 alpha square. Sorry. 1 alpha square alpha. 1 alpha square alpha. Like this we are going. And VABC in the sense it will be VABB VC. VABC in the sense it will be VABB VC. VABB VC. Like this you can write. VA0, VA1, VA2 equals to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha into VABB VC. Okay, so from this, what is VA0 here? What is VA0? 1 by 3 times VA plus VB plus VC. Already we have written one statement, right? What is it? VA plus VB plus VC equals to 3 into VA0. Same thing you got again. Earlier, in the discussion of the symmetrical components, we have written VA plus VB plus VC equals to 3 into VA0. Same result you obtained here again. What is positive sequence voltage VA1? Positive sequence voltage VA1, 1 by 3 times VA plus alpha VB plus alpha square VC. VA plus alpha VB plus alpha square into VC. What is negative sequence voltage VA2? VA2, 1 by 3 VA plus alpha square VB plus alpha into VC. Like this. 1 by 3 VA plus alpha square VB plus alpha into VC. So these formula you have to remember. Okay. So of course, by practicing some problems, we are capable to recall these equations wherever it is needed. Next, same equations I will try to write for currents also, because most of the times in the examination, we use to get the questions in the way of voltages calculation or in the way of currents calculation, most of the times. Okay, that's why I'm thinking in the view of the currents. So I'll take the heading as symmetrical components for currents. Line voltage and line currents also the same analysis is applicable. Simply phasors. For phasors, this analysis is applicable. Okay. All right. Symmetrical components for currents. Symmetrical components for currents. Currents. See, first I'll say IABC vector is equal to A into I012. Simple, na? IABC vector equals to A into I012. If you want to see this, what you have written VABC equals to A into V012. Similarly, IABC equals to A into I012. So, IABC matrix is nothing but IA, IB, IC. IABC matrix is nothing but IA, IB, IC. So I'll write here IA, IB, IC equal to matrix A. Same matrix we have shown earlier, right? What I'm writing IA matrix. It's 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. This multiplied with I012 vector. I012 vector means it is IA0, IA1, IA2. Okay. I012 vector means IA0, IA1, IA2. Else, you can call that IA0 as simply I0. You can call IA1 as simply I1 current. IA2, you can call it as I2 current. So that IA equals to IA0 plus IA1 plus IA2. IB equals to IA0 plus alpha square IA1 plus alpha into IA2. IC equals to IA0 plus alpha IA1 plus alpha square into IA2. And second one I can say Second one, I012 reverse. I012 vector is equals to A inverse matrix into IABC. A inverse matrix into IABC. Okay. What is that I012 we have to call? That is nothing but IA0, IA1, IA2. IA0, IA1, IA2 matrix. IA1, IA2 equal to, so you can write that A inverse as 1 by 3 times of, check this one, 1 alpha square, 1 alpha square, 1 alpha square alpha, and you have IABC here, nothing but IAIB IC. IAIB IC. So like this, you can say IAIB IC. Again, if you want to write the equations, IA0 equals to 1/3 IA plus IB plus IC. IA1 equals to 1/3 IA plus alpha IB plus alpha square IC. IA2 equals to 1/3 IA plus alpha square IB plus alpha into IC. Like that, you can write. Okay. So this is a way how to convert ABC components to symmetrical components. Again, symmetrical components back into ABC. So now we'll be doing number of problems with the help of these equations. So let's take the first problem. So I'm moving to the next slide. How that 1 by 3 came? Vinita, you have to do inversion. You have to do inversion, then only you will get it. So I'm taking some problems here. First question, it's a very, very simple one. I want to make some conclusion based on this question. That's why I'm discussing here. Just read that question and try to give the answers. Yeah, I will upload these additional questions also in the student portal. Maybe today or tomorrow, I will do that upload. Okay. See this. A three-phase system carries the phase currents as IA 100 at an angle 0 degree amperes, IB 100 at an angle minus 120 degree amperes, IC 100 at an angle plus 120 degree amperes. Find the symmetrical components of the phase A current. Find the symmetrical components of phase A current. See, already you have IA current 100 at an angle 0 degree given in the data. Phase B current 100 at an angle minus 120 degree given, amperes. Phase C current 100 at an angle plus 120 degree, amperes. First, you take a positive sequence or zero sequence component you take first. Formula for zero sequence current, IA0. Just you look at the matrix. Look at the matrix. 1/3 IA plus IB plus IC. 1 by 3 IA plus IB plus IC. How much is that sum? 1/3 100 at an angle 0 plus IB 100 at an angle minus 120 plus IC 100 at an angle plus 120 degree. This summation will resulting to be 0. I think. Zero sequence current value 0. Zero sequence current value 0. Well done. What is the current IA1? Positive sequence current. Go with the equation first. 1/3 IA1, 1/3 IA plus alpha IB plus alpha square IC. 1/3 IA plus alpha IB plus alpha square IC. Substitute these numbers. 1/3 IA 100 at an angle 0 degree current alpha 1 at an angle 120 degree. Alpha is 1 at an angle 120 degree. What is IB current? 100 at an angle minus 120 degree plus alpha square 1 at an angle 240 degree. Else you write minus 120 degree, no issue. Alpha square means either you can take the angle minus 120 or plus 240. Multiply to IC 100 at an angle plus 120 degrees. Okay, so from this you can write 1/3 100 at an angle 0 is 100 plus 100, 120, 120 gets cancelled. It will be remains 100 only plus 100 minus 120 plus 120 cancel. That will be 100 only. So it will be 300 by 3. So it will be 100 at angle 0. That's it. That will be 100 at angle 0 degree in terms of amps. That's the current IA1. Next, what is IA2 current? What is the current IA2? 1/3. Go with the formula first. IA plus alpha square IB plus alpha into IC. That's the formula. So 1/3. What is IA? 100 at an angle 0 degree. Okay. What is the alpha square? 1 at an angle minus 120 degree you can take, or plus 240 degree, your wish. IB 100 at an angle minus 120 degree. We have given plus alpha 1 at an angle 120 degree. IC 100 at an angle plus 120 degrees. Plus 120 degrees. Okay, so you can write from this now. 1/3. First number 100 at an angle 0. Second number is 100. Angle is minus 240 degree. Plus 100. Next angle is 240 degree. Plus 240 minus 240. So, of course, if you take up that summation, it will resulting to be 0. It will be resulting to be 0. Right? So, if you are converting these currents into symmetrical components, you are converting these currents into symmetrical components. What you are getting in the symmetrical components? Zero sequence current value is coming 0. Positive sequence current value is coming as 100 at an angle 0 degree. That is nothing but IA itself. Coming as 100 at an angle 0 degree, which is nothing but phase A current. What is negative sequence current you are getting? That is 0. Negative sequence current value will be equals to 0. Okay? Tell me now. How is the original currents ABC given here? Whether these are balanced currents or unbalanced currents? How are the original currents given? Whether these are balanced currents or unbalanced currents? Balanced. Original ABC currents, whatever they have given, those are balanced. Why? In the sense, magnitude of each and every current is equal. Angle between any two is plus or minus 120 degree, either plus 120 or minus 120. So obviously, I can say that these are balanced. And if you are converting these balanced currents into symmetrical components, zero sequence current is 0, negative sequence current is 0. You have only positive sequence component. Okay, so can I say a statement like this? If the system is consisting only positive sequence component, then the system is balanced. Can I say that statement? If the system is consisting only positive sequence, then the system will be definitely balanced. Only positive sequence means positive sequence itself is balanced, right? Okay, right. And I will take one more set of currents here. This one set. Other set of currents, I am giving some other numbers here. IA is something like 70 at an angle 0 degree amperes. IB 70 at an angle plus 120 degree amperes. I am changing the values, angles. Kindly observe. 70 at an angle minus 120 degree amperes. Okay. How these currents we have? 70 at an angle 0. 78 angle 120, 78 angle minus 120. How these currents are given to you? Balanced or not? Definitely. These currents also balanced. And if you convert these balanced currents into symmetrical components, what you get? Zero sequence current. What you get? Positive sequence current. What you get? Negative sequence current. Anybody please tell me, what is zero sequence current? Zero. Zero sequence current will be zero. What is positive sequence current? That also comes to be zero. That also comes to be zero. What is negative sequence current? That will come to be 70 at an angle 0 degree, which is nothing but phase A current. Which is nothing but phase A current. All of you getting this one? So the understanding what you have to make here is, second case, also the system is balanced. But what is the sequence of the system? Negative sequence. The sequence of the system is ACB sequence, or you can say negative sequence. So if you convert these currents into symmetrical components, you get only negative sequence component. You don't get the positive sequence and zero sequence components. So when the system is stable now, balanced now. When the system is balanced, when we can say the system is balanced, if the system is consisting either only positive sequence or only negative sequence, then the system will be balanced one. And if the system is consisting both positive and negative sequences, then the system is definitely unbalanced system. Yeah, all of you getting? Tell me please. Sir, why don't we write IB naught, IB1, IC naught, IC? That's your wish. If you want, you can write Amit Vikram Pujar. If you want, you can write IB naught current, IB1 current, IB2 current also. That's your wish. We are tackling this problem only with respect to phase. Look at the question. Look at the question. What I asked in the question. I am asking only phase A symmetrical components. That's it. If you move to the problems, I will discuss about phase B and phase C symmetrical components also. So now the conclusion, what I am making from this problem is, if the system is consisting, either only positive sequence component, or only negative sequence component, then the system is balanced. And if it consists both positive and negative sequence components, then the system will be unbalanced. Next statement. If the system consists both positive and negative sequence components, then it will be unbalanced. It will be unbalanced. Okay, don't deviate the statement. Jitendra, please look at your statement, what you said. Please look at your statement, what you said. Yeah, so let's take one small problem here. Small problem. Kindly go through this question. Tell me what's your answer here. Yeah. This one. A three-phase system is said to be balanced if it consists. It's a MCQ question. MCQ, multiple choice question, not multiple select. It's a multiple choice question. Multiple choice. Multiple choice means you have to select only one option among these four. If the system is balanced, when the system is balanced, if it is consisting either only positive or only negative. If it's having both positive and negative, it is unbalanced. So option C, what is it? Both positive and negative. If it's having both positive and negative, it won't be balanced system. It's an unbalanced one. We have to strike out these options. Zero sequence components, we keep it aside, right? Option D also strike them. We have to select one among these two. Only positive or only negative. Both answers seems to be correct. A and B, both are seems to be correct. But you have to choose only one option among these two, means you can go for the option A. You can go for the option A. So the correct answer from the option C is A. Because if there is a tie between the positive and negative sequence components like this, you give your vote for the positive sequence components. Means generally I can say if the system is consisting only positive sequence component, then it is balanced. Okay? Mathematically speaking. Yeah, if it's a MSQ, then you can go for A and B. If it's a MSQ question, then you can go for A and B. If it's a MSQ, multiple select question, then you can go for either A is correct or B is correct. Okay. So I'm showing a previous slide. If somebody is writing, please complete it. Why D is wrong? If it's having only zero sequence component, it's not a three-phase balanced system, right? If it's having only zero sequence, then it won't be a three-phase balanced system. Okay, yeah. So the next we'll take one more problem. Kindly go through it. Next problem I am taking up. Find the negative sequence component of phase B current. That is IB2 in the figure shown. Yeah. Just go through this question. If all are present, then it may or may not be. Yes. Only zero sequence can be treated as a single phase system. Yes, you can treat. You can treat that as single phase system. Definitely they will mention is it MSQ or MCQ in the exam. They will mention is it a MSQ question or MCQ question. Yeah. So let's look at this question. Find negative sequence component of the phase B current, IB2, in the following figure. IB2 current you have to calculate. But you don't have a formula directly for IB2. Readily, you don't have a formula for IB2, but you have a formula for IA2. Phase A negative sequence current formula you have. Use that formula first. Then we will see how to convert that into phase B. Very simple. Multiplication of alpha or alpha square will give you. Okay? Yeah. So first of all, I am attempting to find negative sequence component of the phase A current. Solution. IA2 current I need. What is IA2 formula? 1/3. Don't look at the diagram. First you write the formula. Write the formula for IA2. 1/3 IA plus alpha square IB plus alpha into IC. This is a formula for IA2 negative sequence current. 1/3 IA plus alpha square IB plus alpha into IC. Now you have to know the currents IA, IB, IC here. IA, IB, IC currents you have to know. IA current you know already 10 at 9 angle 0 degree. IB current is 0. What is IC current? IC current they have not given in the data. Okay. See, if you apply KCL at this node, so-called neutral, Apply KCL at the neutral. Yeah. So observe here in this diagram. IA current already you have, and this is a neutral junction of the three phases. You can say neutral, and this neutral is not connected to ground. Neutral is not connected to ground, and this side you are getting IA current. This side you are getting zero current. This side you are getting IC current. So three currents are coming towards the neutral, and there is no outgoing path. Sum of the three currents entering to the neutral is equals to 0. Means IA plus IB plus IC equals to 0. Okay. So KCL at neutral will give IA plus 0 plus IC. Summation equals to 0. Then what is that current IC? You can write minus IA. So simply IA you keep as it is for time being. IB you keep 0. IC you keep minus IA. Okay. And you simplify that and try to find out that IA current. Simple. Yeah, I will come to your doubt, Gokul. Gokul is asking that, sir, if any system is having positive sequence and zero sequence, I don't have negative. I don't have negative sequence. If it's having positive and zero sequence, then the system is balanced or unbalanced. Unbalanced. Positive and zero sequence components, if it is having, definitely system will be unbalanced only. If it's having only positive, then balanced. Only negative, balanced. Only zero, we can't say. It's not a three-phase system at all. Okay? Yeah. So let's take up the IA2 equation here. 1/3 IA, I will keep as it is. Alpha square IB, 0. Alpha IC means alpha into minus IA. So you can take that IA common here. You get this IA by 3. 1 minus alpha. So IA number is 10. 10 at an angle 0 in fact. 10 by 3. For that 1 minus alpha, anybody? We have discussed in the phasor diagram, right? 1 alpha square minus alpha. √3 at an angle of minus 30 degrees. √3 at an angle minus 30 degrees. Okay, so this you can get 10 by 3 into √3 means it will be 10√3 at an angle of minus 30 degree in terms of ampere. What is this one? Negative sequence current of the phase A current. Negative sequence current of phase A current. Why I am doing this calculation first? Because formula is available to me. But ultimately, we have to give your answer as negative sequence component of the phase B current. IB2 current we have to calculate. Okay, how to calculate it? Just you draw the phasor diagram of negative sequence. Simply like this, you can draw. I'll show here. Simple phasor diagram, roughly. I can say, yeah, see this. This is A2. This is C2 phasor. And this is B2 phasor. Like this, you A2, B2, C2 phasors are rotating in anti-clockwise direction. It's a negative sequence. And the angular difference is 120 degree. Already you know. 120 degree is an angular difference. Simple. Which phasor you know? A2. You know already A2 phasor. And what phasor we have to get? B2. How to get B2 from A2? Multiply this A2 with alpha. Multiply this A2 with alpha. You get B2 phasor. Okay. Multiply A2 with alpha, you will get the B2 phasor. Therefore, from this, the conclusion is obviously IB2 equals to alpha into IA2. Yeah, up to the time or up to the instant, wherever you get the familiarity with this problems and all, you should be very careful, very, very careful while you are writing the equations. If you commit any mistake, definitely total answer will go wrong. Yeah. So alpha is nothing but 1 at an angle 120 degree. IA2 current 10 root 3 at an angle of minus 30 degrees. Magnitude is 10 root 3. Angle 120 minus 30, that will be plus 90 degrees. That's the phase B negative sequence current. Phase B negative sequence current. So see that we discussed in the phasor diagram earlier. Yeah, I'm really sorry. This magnitude I have committed a mistake. I think it's 10 by root 3. Magnitude is 10 by root 3. So it will come 10 by 10 by root 3 at an angle plus 90 degrees. Okay. Done. Can you find what is IC2 current here in this problem? This is our answer, of course, in the problem. This is our answer in the problem. Can you find what is IC2 current? IC2 current. How much? C2. IC2, nothing but, yeah, look here. IC2 means this A2 we should shift by an angle of 240 degrees. Means alpha square into A2 will give C2. So IC2 is alpha square into IA2, we can see. So alpha square is 1 at an angle 240 degree, and IA2 current, 10 by root 3 at an angle of 10 by root 3 at an angle of minus 30 degrees. So this magnitude will be 10 by root 3 as it is. Angle will come 210 degree in terms of angles. In terms of angles. Okay. Fine. Next thing. Next, we'll take one more problem. One more problem. So it's a previous gate examination question. This question asked in previous gate exam. Go through it. Yeah, just I have to make a small correction in the question. Because typing error it may be, I think so. So it's a EA voltage source. We have EV voltage source here. EV voltage source, and then you have EC voltage source here. So it's plus, plus, plus. Okay, Ariel, you go through this question. We will be solving this question after break. We'll be solving this question after break. Yeah, I'll come to your doubt, Vaishnavi. Yeah, so I have a break for 10 minutes. After break, we will be starting with this problem, and I will explain about neutral current, ground current, and all by this problem. I will compare this with the previous problem what we have done. Okay, yeah, 10 minutes break. 10 minutes break. Yeah, please kindly confirm audio, video on screen once. Please kindly confirm audio, video on screen once. Fine. So let's proceed with this problem. See this. A three-phase alternator generating unbalanced voltages is connected to an unbalanced load through three-phase transmission line as shown in the figure. The neutral of the alternator and the star point of the load are solidly grounded. They have shown in the figure also, solidly grounded. The phase voltages of the alternator are phase A voltage EA, 10 at an angle 0 degree. B, 10 at an angle minus 90. C, 10 at an angle plus 120 degree volts. The positive sequence component of the load current is. Say, simply is asking positive sequence current. In the sense, you have to calculate phase A positive sequence component only. Means you have to calculate IA1 value. Okay? Yeah. So it's a very simple problem. I will discuss this problem in variety of ways by making some modifications. First, let's go with this problem. Yeah. So let's copy this figure. Three-phase network, I can say. Three-phase network to the solution. It's a three-phase network we have. Now, you know, this phase A will carry a current of IA here. Phase B carrying a current of IB. Phase C carrying a current of IC. Like this, we have currents IA, IB, IC. Done. Now, this neutral is solidly grounded, means this neutral voltage will be 0. Alternator neutral voltage is 0. Load neutral also solidly grounded, means load neutral voltage also equals to 0. Now, between these two 0 points, just you can short this one. Both terminals are operating at 0 potential. We can short them together. So like this, we can short. This is what we said, virtual short circuit concept. You can short these two together. Now, if you apply KVL for phase A through this short, phase A through this short, what is IA current? Only one source you have EA by total impedance is J1 plus J1. You will get some value. What is IB current? Again, applying KVL between this phase B and short, EB by J1 plus J2. Similarly, IC. So we are comfortable to calculate the phase currents directly from this circuit analysis, right? So you can write from circuit analysis. From circuit analysis, phase A current is nothing but EA by two impedances summation J1 plus J1. Okay. What is EA? 10 at an angle 0 degree by J1 plus J1 means 2 at an angle 90. Else you go with J itself, no issue. So it will be 5 at an angle minus 90 degree, or else you write minus J5. According to our comfort, I will take any one of these two numbers. It will be in amperes. That current is in amperes, IA. Now, what is IB current? Next slide I am taking. Phase B current. Nothing but EB by, what is this? J1 plus J2 means it is J3, right? J1 plus J2. What is EB current? EB voltage. 10 at an angle minus 90. So it is 3 at an angle plus 90. So 10 by 3. You keep as it is. How much is angle? Minus 90. Again minus 90 means minus 180 degree. Else you can say this one minus 10 by 3 amperes. That's a phase B current, IB. Next one, phase C current. Phase C current, IC. IC. So what you get IC current? EC by J1 plus J3. EC by J1 plus J3. What is EC voltage? What is EC voltage? 10 at an angle plus 120. 10 at an angle of plus 120. Denominator you have J4 means 4 at an angle 90. 4 at an angle 90. Let me write here. 4 at an angle of 90. So it's 10 by 4 means it's 2.5. Angle will be 120 minus 90 means it is 30 degree amperes. I got the three phases currents IA, IB, IC. Now you take up IA1, positive sequence current of phase A. Positive sequence current IA1 Yeah, simple formula. 1/3 IA plus alpha IB plus alpha square IC. 1/3 IA plus alpha IB plus alpha square IC. Substitute the currents, whatever you have calculated, you get the positive sequence current. So I can say IA1 is equals to 1/3 times. So what is IA current? Minus J5. Else you write 5 at an angle minus 90. Plus alpha. Alpha is 1 at an angle 120. Alpha is 1 at an angle 120. And you have IB current. What is IB current you have? Minus 10/3. Else 10/3 at an angle minus 180 or plus 180 degree. Anything you can write. Plus 180 minus 180. Both will be same angles. Plus alpha square. 1 at an angle 240 degree or minus 120 degree. Into IC. What is IC current? IC 2.5 at an angle 30. 2.5 at an angle of 30 degrees. Okay, so you do this calculation, you'll get this answer easily. 1/3. First one you write minus J5 plus it's 10/3 magnitude and angle will be minus 60. Okay, next one. Minus 120 plus 30 means it is minus 90 degree. So 2.5 at an angle minus 90 degree means minus J 2.5. So you can get like this. 1/3 minus J5 minus J 2.5 means minus J 7.5 plus 10/3 cos 60 minus J 10/3 sin 60. Okay, so you calculate that real part and imaginary part. Real part is 10/3 cos 60 degree. 10/3 cos 60 degrees. So that number is 1.665. That's the real part. 1.665 is the real part. Imaginary part, if you take 7.5 plus 10/3 sin 60, it will be minus J 10.38. Minus J 10.38. So you calculate this magnitude and angle because he said that answer in magnitude and angle form. Yeah. So let's move with the next slide. I will be taking up that IA1 magnitude 1/3 into square root of 1/3 into square root of 1.665 square plus it's 10.38 square and angle will come to be tan inverse of minus 10.38 by 1.665. This angle will be in terms of degrees. Okay, you calculate this number. This is a way how we have to do in virtual calculator. This is a way how we have to do in virtual calculator. Okay, so you please calculate this number. So 1.665. So you'll get the magnitude 3.504. Magnitude will be 3.504 amperes. Angle will come minus 80.887 degree. See, you should reduce your calculations. We should reduce your calculations after reaching the final steps. See, after reaching to this step, it's a big, what we call calculation, what I feel numerically. So I will check the options. I will check the options, what they have given. If I see the options, all the options are having different angles. All the options are having different angles. So simply, you try to calculate the angle and you get minus 81 degree close to that. And whichever the option is having angle as minus 81 degree, that is the correct one. All of you getting me? All of you getting me what I am saying you? Simple, simple. Else, you calculate only magnitude. Check which option is matching to that magnitude. Like that, we have to pick up the option. If it's a MCQ question like this. But if it's a fill in the blank question, We have to do the calculation, total calculation. So your answer will be D. Answer will be D. Okay. Next, same question as of previous. Extension will be, what is a zero sequence current and what is a ground current? That's the question. Next one I am asking you. So same as previous question, I will write question. Same data as of previous question. Same data as previous question. Okay, find zero sequence current, comma, neutral current, comma, ground current, and okay, and ground current. Anybody? Tell me answer for this problem. What is zero sequence current INR? What is zero sequence current INR? Formula 1/3 IA plus IB plus IC. 1/3 IA plus IB plus IC we have to take. Okay. You know already IA, it is minus J5 IA. What is IB? Check that IB. Minus 10/3. Minus 10/3 is IB plus. What is IC? 2.5 at an angle 30 degree. 2.5 at an angle of 30 degree. And you have to sum up these three, you will get that INR. Following? Yeah, please tell me, are you following this or not? Yeah, I said earlier itself as a notation or as a standard. If they asked only positive sequence current in the exam, if he's asking only positive sequence current, you find out phase A positive sequence current. That itself is our answer. For example, in this problem, if you find IB1, IC1, no option will match with that. Magnitude will be 3.510. But angle will be different for IB1 current and IC1 current. But you don't find that type of option here. So that we have to go with only phase A component calculation. Yeah, dear Pujar, have you understood this? Yeah, so let's go with this calculation of IA0. 1/3, let's continue in this manner. Minus J5, minus 10/3, plus, you see, 2.5 at an angle 30, na? 2.5 cos 30 degree, plus J 2.5 sin 30. Okay, you calculate the real part of this number and imaginary part of this number. Real part of this number minus 10/3 plus 2.5 cos 30 become minus 1.168. Minus 1.168. Imaginary part minus J5 plus J 2.5 sin 30. This number will be minus J 3.75. 3.75. And you should calculate this angle very carefully. Very carefully. Magnitude will be 1/3 square root 1.168 square plus 3.75 square. That's okay. The angle will come tan inverse of minus 3.75 by minus 1.168. Okay, with the virtual calculator, particularly I am saying you should be very careful in the calculation of that angle. Magnitude will be 1.3091. You calculate angle of this you will get this minus 107 degree, 7.3 degrees amperes. That's the zero sequence current value. That is a zero sequence current value. Okay. And what is a neutral current or ground current here in this problem? See, for example, if you see this diagram, already we have taken this current as phase A load current IA, phase B load current, and then phase C load current. And you know, some of these three currents is flowing into neutral as well as ground. Both will be same now. Neutral current and ground current both will be same. Whatever the current flowing into the ground, that current itself is a neutral current. That is nothing but IA plus IB plus IC, which is 3 times of the zero sequence current. Anywhere, if he is asking us to find ground current or neutral current, you find out 3 times of the zero sequence current. 3 times of the zero sequence current. Okay. So ground current or neutral current, IN or IG, 3 times of IA0 means it is 3 times of IA0, 1.3091 angle minus 107.3 degree. So this magnitude is how much? 3 into 1.3091 means 3.9273 angle will be minus 107.3 degree in terms of amperes. When the zero sequence current will exist in the system? When the zero sequence current will exist in the system? Anybody, please tell me. When the zero sequence current will exist in the system? If and only if the neutrals are grounded and the system is unbalanced. Both neutrals, not only the load neutral, this generator neutral shall also be grounded. Whatever the IN current flowing into ground, that will be circulating back in this manner, dividing into IA, IB, IC. Getting me? So, if the system is unbalanced, first condition is system should be unbalanced. And not only that, if the neutrals are grounded, or if there is a closed path for the current through ground, then there is an existence for the zero sequence current in the system. Following all of you? Right. So if you want, I will write that statement. Zero sequence current exists in the system. Zero sequence current will exist in an unbalanced system. In an unbalanced system, if the neutrals are grounded, or if there exists a closed path through ground, if there exists a closed path through ground, then only it is possible to have the zero sequence current. Okay? In the balanced system, you don't get it. For example, you see in the previous problem, system is balanced or unbalanced in the previous problem? Unbalanced only, right? If you want, I will show that question. This one, system is unbalanced only, but still you don't have zero sequence current. What's the reason? Neutral is not grounded. As a neutral is not connected to ground, you don't get the zero sequence current, even though the system is unbalanced. Okay? If there is no neutral grounding is done, then you don't get the zero sequence current. We are discussing about star connection only, right? We are discussing about star connection. Delta we'll discuss later. Zero sequence current we'll discuss in detail if you go for sequence network analysis. Okay, let's take one more problem. One more problem in this symmetrical component analysis. So it's a question asked in previous IES exam. Of course, it's an objective question. Of course, this question is an objective question. Go through this one. So it's a balanced three-phase load they have mentioned here. There are 3 wires. These are terminals ABC. Terminals ABC. It's a triple pole switch. Triple pole switch in the sense we have only one hanger, and whenever you move that hanger down or up, whatever it is, at a time all the 3 switches will be closed. 3-pole switch, you can say something. 3-pole switch. That's what they said. Okay, with one shot we can close all the 3 poles. Next. See, a balanced 3-phase load is supplied from a 3-phase supply. They have not shown the supply here, but still you have to consider it according to the state. The contact in line C, this is a line C, it's a contact. It's a contact in line C. Of the triple pole switch, contactor fails to connect. When switched on, means he is saying that this triple pole switch was closed. After closing this one, A was contacted to the load, B was contacted to the load, but C was not contacted properly. Means it is acting as open mode. If it is acting as open mode, how much is current in C? 0. Okay. Now he is saying that if the line currents in the lines A and B record 25 amperes each. Line A current is 25, line B current also 25 we say. Then the positive sequence component of the current is. He is asking simply positive sequence component. Which phase current you have to find here? Which phase positive sequence component you have to find here? Phase A. Phase A positive sequence component we have to calculate. Okay. See, according to the assumption, what we take, we used to get number of answers for this problem. Exactly. We used to get number of answers for this problem according to the what we call assumption what we are going to take. Let us say, first, listen here, listen. Solution. One of the common assumption what I am making now is source neutral is grounded. You assume that. Source neutral was grounded. That's the first assumption I am making. Source neutral grounded. This is the assumption. First assumption we are making here is source neutral was grounded. What about load neutral? What about your load neutral? Is it grounded or ungrounded? Grounded or ungrounded? We don't know. First assume that it is grounded. Load neutral also grounded. Okay, let me write. First case, load neutral also grounded. Load neutral also grounded. To understand this problem, I want to show this in the manner of 3-phase network. I want to show this problem in the manner of 3-phase network. Be clear about this one. At what stage you are? Learning stage. If you are at the learning stage, you should have a capability to look into the problem in different dimensions. Should look into the problem in different dimensions. Okay, that's why I'm thinking about this problem in different ways, and we will check how the answers will. Load neutral is grounded is an assumption. In bracket assumption. Assumption. Now I will draw the three-phase diagram. So it's a three-phase source, phase A voltage, and it's a phase B voltage of the source, and it is phase C voltage of the source. And already we mentioned that this neutral is connected to ground, leave it. And these are the outcoming lines, ABC, you can call if you want. ABC. Okay, I will show load here, three-phase load. Load neutral also grounded, we said, na? Okay, so this load is saying load. Okay, and this is phase A terminal of the load, and it is phase C terminal of the load. I'm showing here phase C terminal of the load, and this is phase B terminal of the load. Phase B terminal of the load. Okay, now this load neutral also grounded, so I will show something like this. It's also grounded. Now, one of the assumption you can consider now, one of the assumption, strictly speaking, first phase voltage is some magnitude with some angle 0 degree, source voltage. Second phase voltage, some magnitude at an angle minus 120 degree you assume. Third one is magnitude C at an angle plus 120 degree. All magnitudes are equal, you say. All magnitudes are equal. Mod VA source voltage, mod VB source voltage, mod VC source voltage. All the three are equal. Balanced source, and angles will be 0 degree, minus 120, plus 120 degree. Load is also balanced. Load is also balanced. But unfortunately, all of you followed up to this point? Please kindly tell me. Are you following up to this point? Okay. Yeah. Next. Listen here. Now, what we are assuming is A is connected, B is connected, C is open. Of course, he said in the problem, not assumption strictly. A was contacted, B also contacted, C was open. C was open. Now, you observe here, this neutral is grounded, means operating at 0 potential, right? This neutral is grounded, means it's operating at ground potential, 0. This neutral also grounded, means operating at 0 potential. Kindly observe my words, what I am saying. First neutral is grounded, operating at 0. Second neutral also grounded, operating at 0. Okay. Phase A will carry some current IA. Phase B will carry some current IB. But phase C current equals to 0. Phase C current will be equals to 0. Getting me? Now, as a neutral voltages are 0, you can short those neutral voltages together. Following all of you. By shorting them, IA current is nothing but simply this voltage by load impedance. Voltage by load impedance. What is IB current? Phase B voltage by load impedance. All these three impedances are equal. You assume that load is resistive for time. You assume that this load is resistive of value R. Resistive of value R. And he said clearly IA current in the problem. How much? 25. So obviously, magnitude of this IA current will be 25. And angle I will assume as 0 degree, because this voltage angle 0 degree and this assumed as resistor load. So obviously, overall angle of this IA current will come to be 0 degree. That is nothing but voltage angle. What is IB current now? Magnitude will be remain same, 25 only, because he said in the problem, right? B also recording 25 amperes. B also recording 25. But how much is the angle for that? How much is the angle for that current? That will be the voltage angle of phase B, means minus 120 degree you should take. Minus 120 degree. And of course, the phase C current will be equals to 0. phase C current will be equals to 0. Yeah, all of you understanding this? Please tell me. I said listen properly. I said you listen properly. Voltage VA at an angle 0. Resistance R, load. Then what's the current? VA at an angle 0 by resistance. Magnitude of that current is 25. The angle is voltage angle itself, 0 degree. Because of resistive. Phase B current, VB at an angle minus 120 by R. Magnitude is 25, you said in the problem. Angle will be voltage angle only, minus 120 degree. This is one way of selecting phase A, phase B, phase C currents. With the help of these three currents, calculate positive sequence current of the system. Means IA1 value you have to calculate. Okay. So I can say positive sequence current here, IA1, which is nothing but 1/3 IA plus alpha IB plus alpha square IC. Substitute the numbers. 1/3 IA. What's IA current? 25 at an angle 0. 25 at an angle 0 plus alpha 1 at an angle 120 degree. IB current 25 at an angle minus 120 degree. What is IC? 0. So it will be 1 at an angle 120, 25 at an angle minus 120. So it will be 25 at an angle 0. So 25 plus 25, that is 50, 50 by 3. Angle will be 0 degree only. Angle will be 0 degree. How much is that number? 50 by 3? 16.667 amperes. 16.667 amperes at an angle of 0 degree amperes. This is one possible option. This is one possible option. Do you have that option in that ABC given? No, you don't have it. 16.667 at an angle of 0 degree, we don't find in the options A, B, C, D. Okay, this is one answer. This is one answer by taking some assumptions. Next assumption, look here kindly, look here. Next assumption, what we will do is, this load neutral is ungrounded, I will take. If the load neutral is ungrounded, I should not say this potential is 0. I should not say this potential is 0, and I don't have any neutral current also. I don't have any neutral current also. At the time, whatever the IA current flowing in this direction will circulate through phase B out. Will circulate through phase B. Okay? Anyhow, I will show that also. Same diagram I am repeating. Load neutral ungrounded. Load neutral ungrounded. That's the third part. Sorry, second part. Second part of the problem means second way of solving the problem. Load neutral ungrounded. Ungrounded. So this is that diagram I have given earlier. Okay. So now don't bother about the angles and all. Please kindly forgive me. I'm not taking angles in a proper way. So I am removing this neutral point grounding. So this voltage will no more 0. Neutral voltage definitely not equals to 0 here. This neutral voltage not equals to 0. But this neutral voltage is 0 because it is grounded. It's grounded. So this neutral voltage is 0, but it is not grounded. Neutral voltage will not be equal to 0. So now you can see, by the application of KCL at this node, IA entering, IB entering, IC 0. Means IA plus IB plus IC equals to 0 at the load neutral. Okay? Yeah. So you draw this one quickly. Draw this one quickly. Draw this one quickly. He said here balance, right? Balanced load. Balanced load. Balanced supply also, of course. Okay, see from this, KCL at neutral will give IA plus IB plus IC, this summation is equals to 0. Okay, I'll keep IA. What is IB? IB, we have some number, we don't know that. IC is 0, means you can write this phase B current as negative of phase A current. Phase B current is negative of the phase A current. Negative of the phase A current. Negative of the phase A current. See, now let us assume that that current IA is equals to 25 magnitude, angle is 0 degree. This is assumption. I'm saying it's an assumption. It's an assumption. 25 magnitude is said in the problem. The angle I am taking 0 degree as an assumption. Now you calculate IB. Of course, it is minus IA according to the discussion what we are taking. Now you calculate IA1, positive sequence current. Now IA1 current, I have to do formula. Once you can repeat it, 1/3 IA plus alpha IB plus alpha square IC. Alpha square IC. So you substitute these numbers. So you can call IA1 here 1/3 IA. You keep as it is first. Alpha IB means minus alpha IA you can write, because IB replaced with minus IA. IC value 0. You can take IA common. IA by 3 into 1 minus alpha. IA number 25 at an angle 0 degree. What is 1 minus alpha? 1 minus alpha means it is √3 at an angle minus 30 degrees. So you can get this like 25 by √3. Angle will be minus 30 degree in terms of amperes. What is that number 25 by √3? 25 by √3. This number is 14.43 at an angle minus 30 amperes. 14.43 amperes at an angle minus 30 degree. Do you find this type of option in that ABCD? Are you finding this type of option? Yes, you are finding as option B. As option B. Okay. So according to this assumption what we made, your answer might be B. Your answer might be B. Why you are getting different answers according to different assumptions means there may be a lack of clarity in the question. That's the reason. Because definitely he should mention, if he is giving this type of question means he should mention in what connection that load is. Is it a star connected load or delta connected load? If it is star, is it grounded or ungrounded? That they have to mention in the problem. That is missing in the question. That is missing in the question. So first we assumed that our source is star connected, grounded. Star connected, grounded I assume. Then I assumed that load neutral. Load is also star connected, neutral is grounded. We have done some solution. We got some answer which is not in the options. Left aside. Next, I assumed that this load neutral is ungrounded and I have taken IA current. IB current is negative of IA and we got some answer, but we are finding this one in the options. For example, if the load is delta connected, the load is delta connected. That's the third case, third possible case, what you can see. Okay. Yeah. Let me draw that also quickly. Let me take up that also quickly. Load is delta connected. Third one. Load is delta connected. Yeah. See this. So I am removing this load completely. Okay. Show. Load in the delta connection. Because of that lack of clarity in the question, we are doing this one in many ways. Of course, we have to learn something from each and every step. This is a phase A connection. Phase B connection is this we have. Phase C connection is this one. Again, you see, it's a delta connected load, that's fine. C current is 0. It's not carrying any current. Now, you can make an assumption if you want like this. IA current is entering to this point. Maybe it is seeing two paths of current flow. Look here. Look the board. IA current is entering, dividing into two parts. This is one part and this is the other part. You assume it is you will get some confusion if I take IA1, IA2. I'll take this is something like I1, I2, some currents. I1, I2 plus summation is nothing but IA. See, this I2 current is coming like this. This current is 0, and this I2 current going out like this because this channel current is 0. And whatever the I2 current coming in this direction, and this I1 current is coming, that I1 plus I2 is going out. I'm really sorry. I think I have taken as a different one. Okay, look here. I1, I2 currents. I1 current is coming like this, and this current is 0 now. This current is 0. So whatever the I1 current you have, that is going into this phase directly. And I1 current is going, I2 current is going, that is becoming sum, and that I1 plus I2 summation is going out like this. Means IA current is going out like this, and means IB equals to minus IA here. IB equals to minus IA. I don't know whether you have understood this circuit analysis or not. Yeah. So from this, also you can make a comment that phase B current equals to negative of the phase A current. And if you assume again IA equals to 25 magnitude given in the data, the angle we are assuming 0 degree, then what is a positive sequence current you get? Same as a previous solution. So it will be 14.43 at an angle of minus 30 degree in terms of angles. Again, I can say the option is B from the ABCD. Okay, but generally in the GATE examination, you don't find this type of confused question, lack of clarity question. This type of question you don't find in the GATE examination. Okay, because we are having a weapon to question them. If they have given some question, if there is any missing data, right? They are responsible for it. That's why they are very clear to give the question in the present days of the GATE examination. Okay. Let's take one more simple problem. I will move to next slide. Yeah. Look, next problem I will take the. Let me check, is it or not? Yeah. So it's also a previous GATE examination question only. Previous GATE exam question. Kindly go through it. Yeah. In an unbalanced three-phase system, the phase current IA 1 at an angle minus 90 degree per unit. Negative sequence current IB2 4 at an angle minus 150 degree per unit. Zero sequence current IC0 3 at an angle 90 degree per unit. The magnitude of phase current IV is dash per unit. Magnitude of the phase B current is how much? Okay. See, from the data what they have mentioned, current in the phase A, IA, said it is 1 at an angle minus 90 degree, okay, per unit. And next one, He said IB2 current. How much is it? It is 4 at an angle minus 150 per unit. And then IC not zero sequence current, IC not 3 at an angle 90 degrees. Let's go with the target. Let's go with the target. What we have to get? Phase B current you have to calculate. You write phase B current in terms of symmetrical components. Right? Phase B current in terms of symmetrical components. Phase B current. IB equals to, either you can write in terms of A or you can write in terms of B. That's your wish. I am writing in terms of A. IA naught alpha square IA1 alpha IA2. Like this, we have the formula. What is IA naught? That's nothing but IC naught. You can get it easily. What is IA1? It didn't mention positive sequence component in this at all. IA2, I can get it from IB2 current. Okay, right. So first you write IA naught is nothing but the value of IC naught. That value was 3 at an angle 90 degrees. 3 at an angle 90 degrees. Okay. So you know already B2 current. You know already B2 current. How to get A2 from that? You know already B2 current. How to get A2 current from that? So you draw that phasor diagram negative sequence in a rough way. In a rough way. So I'm showing like this. This is A2 phasor. This is C2 phasor. This is B2 phasor. Negative sequence. Negative sequence. A2, C2, B2. Okay. Which phasor you know? Which phasor you know? B2 I know. B2. I have to get A2. B2 value I know. I have to get A2. Means B2 if you shift by an angle of 240 degree. B2 if you shift by an angle of 240 degree, we will get A2. Means A2 is equals to alpha square B2 you can write. B2 if you shift by an angle of 240 degree, you will get A2. So A2 equals to alpha square B2. So now you can write IA2 nothing but alpha square IB2. IB2. Now, so you can say alpha square 1 at an angle 240 degrees, IB2 4 at an angle minus 150, means magnitude will be 4, angle 240 minus 150 means it is a 90 degree per unit. 90 degree per unit. Okay. Next we got IA2 current. IA naught also we got. Now we have to get IA1. IA1. I know already IA, right? What is the IA formula? IA equals to IA naught plus IA1 plus IA2. From that, we are capable to get the IA1 current. Okay. Yeah. So now, right, as phase A current is nothing but IA naught plus IA1 plus IA2. Okay. So IA1 current is nothing but phase A current minus zero sequence current plus negative sequence current. So IA, how much is IA? 1 at an angle minus 90 degree is IA. Minus of what is IA1, IA2? Sorry, IA not. IA not, IA2. Good. IA not 3 at an angle 90. IA2 4 at an angle 90. So first one at an angle minus 90, you can write minus J1 minus, it is J3, J4, J3, J4 means J7, means it is minus J8 per unit. IA1 current is minus J8 per unit. Minus J8. Okay, next. After getting this IA0, IA1, IA2 currents, you can find IB, simple. So now you can say IB current is equal to IA0. IA0, you have 3 at an angle 90 degree. 3 at an angle 90 plus alpha square IA1. Alpha square means 1 at an angle 240 IA1 current how much? Minus J8 means you write 8 at an angle minus 90 plus alpha 1 at an angle 240. Sorry, 1 at an angle 120 alpha into this IA2 current is 4 at an angle 90. 4 at an angle 90. So you can get from this, it is J3 plus it is 8 at an angle 240 minus 90, that will be 150 degrees plus 4, 90 plus 120, that will be 210 degrees. You expand it. 8 cos 150 plus J 8 sin 150 plus 4 cos 210 degree plus J 4 sin 210 degrees. Okay, you calculate the real part of this whole and imaginary part. 8 cos 150 plus 4 cos 210. Real part is minus 10.392. Imaginary part 3 J3 plus 8 sin 150, 4 sin 210. It will be plus J5. J5. But he is asking only magnitude of that current. Phase B current, only magnitude he is asking. So if you take this magnitude IB, it will be square root of 10.392 square plus 5 square. So if you calculate this, 10.392 square plus 5 square, 11.53 per unit you will get. 11.53 per unit. That's a phase B current. You can substitute directly IB2 also. That's your wish. That's your wish. Why you're asking me again? If you know it already, you substitute. That's it. Okay. Fine. So alpha does not have any units. It's just a phase shift operating. Alpha, it's just a phase shift operating. Does not have any units. Yeah. So till now, we have seen some problems, how to convert what we call 0, 1, 2, so-called symmetrical components to ABC we have done, and ABC to symmetrical components also we have done. So next I'm going to take up one small topic in the symmetrical components, that is expressing complex power in terms of symmetrical components of voltage and currents. Expressing complex power in terms of sequence components of voltages and sequence components of currents. Okay, yeah. So I am taking the next heading. Next heading here. Complex power in terms of symmetrical component of voltages and currents. Voltages and currents. So this does not mean that we are applying symmetrical components for the power. This does not mean that we are applying the symmetrical components for the power. Okay. So go with this heading, what I said. I will be elaborating this heading now. First of all, what is the formula for complex power? Maybe three-phase complex power, you can say. Three-phase complex power formula I want to write first. Three-phase complex power formula. So it will be V into I conjugate. Complex power formula in the sense it is V into I conjugate. Three-phase complex power means you might be thinking in a view to write 3 into V into I conjugate. But the 3 into VI conjugate is valid only for a balanced system. If it's an unbalanced system, we should take phase A complex power plus phase B complex power plus phase C complex power. That summation we should consider. So I will be writing SABC, three-phase complex power SABC equal to phase A complex power VAIA conjugate, phase B complex power VBIB conjugate, phase C complex power VCIC conjugate. Like this we should say. Okay. See, writing this complex power in terms of symmetrical components of voltage and currents is nothing but simply write VA in terms of symmetrical components, IA in terms of symmetrical components. Similarly, VB, IB, VC, IC. That is the meaning of the writing complex power in symmetrical components. I want to write this single term, what we have, summation of 3, in matrices form. In the matrices form. Yeah, kindly observe this. VA, VB, VC. Okay, it's a row vector multiplied with IA conjugate, IB conjugate, IC conjugate, column vector. Okay, so row vector VA, VB, VC, column vector IA conjugate, IB conjugate, IC conjugate. What do you get now? VIA conjugate plus VBIB conjugate plus VC, IC conjugate. That is a SABC complex. Okay, today only we have taken up some what we call some relations. Some relations we have taken today itself. I want to recall those relations. Okay, just see. Voltage vector VABC voltage vector, we have written it as VAVBVC. Similarly, current vector IAVC, we have written that as IAIBIC. So my intention is to discuss about this here is, it's a row vector, right? It's a row vector, but column vector we have taken as a notation of VABC. Now what will happen to row vector? VABC transpose. So this we can replace as VABC transpose. But IABC column vector is okay. IABC, but you have conjugate for each and every term. Okay. So by that means, we are going to rewrite this SABC in matrices form. So therefore, you write like this. Therefore, SABC complex power equals to VABC transpose into IABC conjugate. VABC transpose into IABC conjugate. Now, simply you try to replace this VABC vector in terms of symmetrical components, because today itself we have written VABC vector is nothing but A into V012. I think all of you know about this. A into V012. And similarly, IABC vector is nothing but A into I012. A into I012. That you simply dump into that SABC equation. That is simply dump into the SABC equation. What you will get from this? SABC equals to VABC transpose means A into V012 whole transpose multiplied with conjugate of this IABC. Na? So A conjugate into I012 conjugate. A conjugate into I012 conjugate. Like this you can write. A into V012 whole transpose into A conjugate into I012 conjugate. And if you take up this transpose, you will get here V012 transpose multiplied with A transpose, A conjugate, I012 conjugate, I012 conjugate, like this unit. Okay. Are you an electrical engineer, Mr. Anamel Sachendi? Why conjugate you are asking me? Huh? Why not V conjugate I? You might have studied V into I conjugate as a complex power. If time permits, I will explain it, how it's coming. V into I conjugate. Yeah. So let's continue with this V012 transpose, A transpose into A conjugate into I012 conjugate. That's okay. A transpose A conjugate, I will take specially. A transpose A conjugate, I will take specially, and I will try to write that matrix. Right. So A transpose into A conjugate. It's a very simple one to write. What is matrix A? Matrix A only. 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. You apply transpose for this, what you get now? What's the transpose of this one? 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. Transpose, it will be same, right? After applying transpose to this matrix, you will get same matrix as it is. And you have to take A conjugate. What is A conjugate here? A conjugate means each and every term you have to apply the conjugate. 1, 1, 1. Okay. 1. What is alpha square conjugate? You get alpha. Alpha conjugate will give alpha square. Just now we discussed about that alpha. Alpha conjugate 1. Okay. Alpha conjugate is alpha square. Alpha square conjugate will be alpha. Okay. You take this matrices multiplication. Take these matrices multiplication. See, if you take up this matrices multiplication, you may get 3, 0, 0, 0, 3, 0, 0, 0, 3. Like this you will get. 3, 0, 0, 0, 3, 0, 0, 0, 3. Okay, that you substitute here. Maybe this 3, 0, 0, 0, 3, 0, 0, 0, 3, you can write this as 3 times of identity matrix. That identity matrix, I am using a symbol U, because I we are using for current now. That's why I am using a symbol U, identity matrix. Okay, now I will rewrite that complex power SABC. You please complete it if you are still writing. You are still writing, please complete it. So I'll wait for 5 seconds. Please complete. Okay, so I'm moving to the next slide. SABC complex power equals to, you can write V012 transpose, V012 transpose, A transpose into A conjugate is 3 times of identity matrix, and here you get I012 conjugate. So that identity matrix multiplied with current, it will come current vector only. 3 is a scalar, you can take it out. So it is 3 into V012 transpose into I012 conjugate. I012 conjugate. SABC. SABC. Okay. Next, listen here. See, earlier we have written SABC equals to VABC transpose into IABC conjugate. SABC equals to VABC transpose into IABC conjugate. In the similar terminology, this V012 transpose into I012 conjugate, I will write it as S012. S012. Okay. So SABC equals to 3 times of S01. S0, 1, 2. This is one simple conclusion you can take. Okay, anyhow, we don't stop at this point. We will expand these matrices and we will try to write the equation in the file. Yeah, so let's continue. SABC is equals to 3 times V012 transpose. You can write it as VA0, VA1, VA2 row vector multiplied with I012 conjugate is IA0 conjugate, IA1 conjugate, IA2 conjugate. Like this you can see. Now, if you multiply these matrices, finally, what you will get here is SABC is equals to 3 times of VA0, IA0 conjugate, IA0 conjugate plus VA1, IA1 conjugate, IA1 conjugate plus VA2, IA2 conjugate. Like this, you will get this SABC, complex power SABC. In terms of symmetrical components of voltages and currents. In terms of symmetrical components of voltages and currents. Okay. Next, I'll try to tell one more simple conclusion here. Kindly go through it. One small conclusion with respect to this complex power calculation in terms of symmetrical components. Moving to next slide. Yeah, it is. It's a system A, B, C. I'm showing simply some phasors. Maybe it's a combination of voltage and currents. You don't need to bother about it. Simply it's a ABC system I am showing. It's A, like B and C. ABC system. This you have converted into positive sequence plus negative sequence plus zero sequence. Okay. Positive sequence I am showing A1, B1, C1. Positive sequence. Negative sequence I will show A2, C2, B2. Plus zero sequence I am showing simply like this A0, B0, and then it is C0. Like this I have shown ABC. ABC system convert into positive plus negative plus zero sequence. Okay, simple, very, very simple question I am asking you. What is a complex power drawn because of the positive sequence voltage and currents? Now, what is a complex power due to the positive sequence components of voltages and currents? That's the question. You take phase by phase, phase A, phase B, phase C, you take sum. Okay, what is the phase A complex power? Simply VA1 into IA1 conjugate. Yeah, please tell me, are you following this or not? Are you following this or not? Yeah. See, for the positive sequence, I am thinking. Positive sequence, I am thinking. VA1, IA1 conjugate, phase A. What is phase B? VB1, IB1 conjugate. Phase C, VC1, IC1 conjugate. But you know, these are balanced, right? These are balanced in the sense, if you take some of these three complex powers, phase A, phase B, phase C, it will result into 3 times of VA1, IA1 conjugate. Will result into 3 times of VA1, IA1 conjugate. Similarly, you see negative sequence. VA to IA2 conjugate. VB to IB2 conjugate. VC to IC2 conjugate. Again, these are equal. These three complex powers are equal. That you can write as 3 times of VA to IA2 conjugate. And again, here also, the 3 complex powers are equal. It will be 3 VA0, IA0 conjugate. VA0, IA0 conjugate. Like that we can write. Okay. What is complex power in your actual ABC system? As it's the unbalanced one, we should write phase A complex power plus phase B complex power plus phase C complex power. Sorry. Phase A complex power plus phase B complex power plus phase C complex power. That is a complex power in the ABC system. And if you sum up, listen please, listen kindly. If you sum up the complex powers obtained from the sequence network analysis. Sequence analysis. Positive sequence complex power 3 VA1 IA1 conjugate. Negative sequence complex power 3 VA2 IA2 conjugate. Zero sequence complex power 3 VA0 IA0 conjugate. If you take that summation, that is nothing but the three-phase complex power of the unbalanced system. Three-phase complex power of the unbalanced system. This property is going to be called as power invariance property. Power invariance property. Very simple, very simple. Listen here, listen. Power invariance in the sense, even after using symmetrical components, whatever the complex power you calculated with the help of symmetrical components, that complex power and the original complex power or original system complex power, both are equal. Means the symmetrical components transformation technique is not changing the complex power value. Not changing the complex. Original complex power means what you should say? This one only, right? This is my original complex power. And complex power calculated with the help of symmetrical components is this one. Both are coming equal. In the sense, the symmetrical components transformation is not changing the value of the complex power. This property is going to be called as power invariance property. Power invariance property, right? So this property is going to be called as power invariance property in symmetrical components. Property of symmetrical components transformation. Symmetrical components transformation. Power invariance property of the symmetrical components transformation. Yeah. So we will stop at this point. Beyond this, we have to discuss some problems on this complex power and all. It may take some time because it's a linked concept. Tomorrow we will discuss those problems. Tomorrow, I think, class schedule. It will be from 2 p.m. to 9 p.m. Tomorrow Sunday, 2 p.m. to 9 p.m. So after completing those problems, I will enter into sequence networks in a way. Okay. So if you have any doubts, you please raise your hands. So I'm making all the hands low. Please raise your hands now. Please raise your hands. Yeah. Pujar, tell me, Pujar, what's your doubt?
Good evening, sir. Sir, in the previous question...
Please don't keep the messages continuously. Repeatedly, you don't put the same message in the Q&A. Once
Okay,
if I put, definitely I will look into it. Okay?
Yes, sir.
Tell me, please.
Sir, in the question where you had discussed different cases, how do we know that the source is not in the delta connection?
That's a lack of clarity, I said, right, in the question.
Okay, sir. Sir, and how are these two?
Because of that lack of clarity only, we used to get different answers for the same question.
Yes, sir.
Okay.
And sir, how this power invariance, how both of these are equal? Like, do we have to prove it, or is it just given that it is equal?
See, you use the what we call symmetrical components transformation.
Yes, sir.
After using the symmetrical components transformation, you calculated positive sequence complex power, negative sequence complex power, zero sequence complex power.
Yes, sir.
What is the total complex power you are getting? 3 into VA1 IA1 conjugate plus 3 into VA2 IA2 conjugate plus 3 into VA0 IA0 conjugate.
Yes, sir.
Okay, this power is becoming equal to original system complex power. That's what we derived here.
Yes, sir.
SABC equals to what? 3 VA0 IA0 conjugate plus 3 VA1 IA1 conjugate plus 3 VA2 IA2 conjugate.
Yes, sir.
So that equation we are getting in the sense complex power calculated with the help of symmetrical components remains same as the ABC complex power.
So, sir, we can say this as law of conservation of energy in simple terms.
That also you can say if you want. That also you can say. But this law of conservation of energy or power may not be satisfied by all transformation. We are using one transformation as symmetrical components transformation. And we do have some other transformations like Parkes transformation, DQ0 transformation, different transformations are there. All those transformations may or may not satisfy the power invariance property, but our symmetrical component transformation is satisfying it. That's the point we have to highlight.
Yes, sir. And sir, one more thing, sir, tomorrow actually from 9 to 12 we are having one class for measurement, and then from 2 to 9 again
How
we
many
are
days it
having.
is? Can you tell me how many days it is?
Sir, as of now it is given for tomorrow.
Only tomorrow.
Yes, sir, as of now, like whatever schedule is visible.
Is it the
to
last
us right
class
now.
for measurements?
Mostly, sir.
Then how you can't accept it?
Sir,
If it's only one day,
So because the faculty had said that the measurements will be covered in 2 phases. So this is the end of the first phase. The second phase, when it will start, we don't know. That is the reason.
no, they may start soon. Maybe it may be with respect to the faculty problem and all. Okay.
Okay, sir.
Okay. We do have our own personal issues. Okay. Yeah. Abdul Rahman. Abdul Rahman.
Hello, sir.
Tell me.
Sir, can you please repeat the last one, sir? Power invariance property.
Just now I explained, right?
Yes, sir. Yeah, I explained, but
What's the
it has
doubt
been
you have?
somewhat. Yeah, how it will be equal? You see? So can
That's
you please
what we
repeat once
derived
again?
here.
Yeah.
You have to link up this derivation with this diagram.
What I'm saying is 3 into VA1 into IA1 in the positive. I think so, sir. I think so. In positive sequence, 3 into VA1 into IA1. And the negative sequence.
VA1 into IA1 conjugate.
Yeah, so I have doubt regarding how you are taking the conjugate instead of IA1.
No, these are complex value of voltage phasor, current phasor. Complex power formula is V into I conjugate, right?
Acha. Sir, one more thing is, while you are discussing regarding positive, negative, and zero sequence, it is quite related to fundamental frequency, third harmonic frequency, and fifth order harmonic. I'm sorry, fifth order harmonic in transformer, right, sir? It is similar. And what I'm thinking is, it is similar.
Why you taken those harmonics here?
Due to, sir, you have told that in not only in this subject, whatever the load is, the load is receiving only fundamental frequency, right? Fundamental.
No,
That's
here. First, you be clear about this difference between Fourier series and symmetrical components.
Due to recently the transformer subject has been completed.
Listen to me first. Please kindly listen.
Okay.
What you have done in Fourier series?
I'm sorry, sir.
What you have done in Fourier series generally?
I'm sorry, sir. I didn't listen the math subject. It has not started yet. That's why I didn't know.
No, you might have
regarding
studied maybe in transformers also, right? As you said, you studied recently transformers.
in non-linearity concept.
Hmm.
I think so. In
See, a
non-linearity.
non-sinusoidal waveform is going
Yeah.
to be converted into number
Yeah.
of sinusoidal waveforms of different frequencies.
In the
But
transformer
here
section.
there is no concept of harmonic here.
And what I'm saying is it
A
is
pure
similar.
sinusoidal signal is going to be converted into sum of three sinusoidal signals of same frequency.
Okay.
That is symmetrical components transformation.
Okay, sir.
Okay, so you don't have any change in the frequency from positive sequence to negative sequence and negative sequence to zero sequence. All are operating at the same frequency.
Achha.
Okay,
Okay, sir.
so that is a difference you have to understand between symmetrical components and Fourier series. In Fourier series, non-sinusoidal signal is going to be converted into number of sinusoidal signals of different frequencies. But here, a pure sinusoidal signal is going to be converted into three sinusoidal signals of same frequency.
Achha, that is the main difference.
Main difference between the symmetrical components and Fourier series.
Okay, sir.
Okay,
Okay, sir. Sir, one more doubt is there.
then we can.
Sir, a problem has been done in today class regarding a three-phase alternator generating due to alternator and load side has been grounded, right? In that problem, can we found directly as I is equal to E by Z for each phase per phase? Can we can we calculate like this, sir? I is equal to EA by Z. IB is
Is it
equal
today's class or yesterday class?
No, sir, just half an hour, yeah, 45 minutes back. Today's class only.
Is it this problem?
And yes, sir. Yeah, this problem.
This one?
Yes, sir. This problem only.
Okay, tell me. What's the doubt you have?
What I'm saying is, for each phase can be calculated as IA per phase equal to EA by ZA due to the impedance has been given in the problem.
Impedance they have not given in the problem, right?
Reactance? No, sir. J, I'm sorry, sir. Go to previous page, sir. Can you please?
This one?
No, sir. No, sir. Yeah, this problem. In
okay.
this problem,
Hmm.
I'm considering the reactance as a load. Hello.
Okay. Tell me.
Yeah,
Go ahead, please.
Yeah. For each phase, I'm considering. I have to. I'm calculating as IA is equal to EA by this whole reactance, and IB is equal to EB by whole reactance.
Okay.
So just like that. Can I calculate it like this?
For what problem?
For this problem.
That's what I have also done, right? In the solution also, I have done the same thing. Abdul Rahman.
Sir.
Tell me where you have doubt in this.
Okay, sir. Okay, I have understood. Okay, sir. Okay, sir. One more thing is there. Sir, the equations are somewhat confusing, sir. Due to initially you have taken 1 and alpha square and alpha. After that deriving, we have get the IA naught, IA1, IA2. The alpha has been varying from alpha to alpha square.
Alpha is not varying from alpha to alpha square.
Based upon the
remember that matrix, what I said.
Sir, based upon the phase difference, phases.
We have to remember that matrix what we have discussed.
Sir, can you please repeat the alpha concept, sir?
Phase alpha shift concept in the sense this phase shift operator.
Yeah, phase shift operator. Next,
alpha is going to be a phase shift of 120 degree for any phasor without changing the magnitude.
Okay, sir. So go to for next phase.
Okay.
Phase, what we say, the phasor diagrams has been displayed in your page. That's
this one.
Yeah, sir. This one. So can you please still?
VA1 voltage you have here.
Okay.
You multiply this VA1 with alpha, what will happen?
Alpha into VA.
That's okay. That I also can tell. Alpha into VA1 you get. What will happen to that phasor?
What will happen is I didn't understand.
What alpha will do?
It will go. It will turns into balance by using alpha.
Just read this statement.
Without changing the phasor magnitude.
Okay. If I multiply this VA1 with alpha, what will happen?
Without changing the magnitude, it has been changed. It is
Will be
goes for
shifted by
120 degrees.
120 degree. Means this alpha into VA1 will go along this axis. Means that is nothing but VC1.
Okay, sir.
So VC1 is nothing but alpha into VA1 we can write.
Okay.
So now you multiply VC1 with alpha.
VB1 will be.
Alpha into VC1 means what? It will be shifted by an angle of 120 degree.
Okay.
Means it will come on the B axis.
Achha.
So alpha into VC1 is nothing but VB1.
Okay, sir.
So VC1 you can replace with alpha into VA1.
Sir.
So it will be alpha square into VA1.
Achha. For a positive sequence, right, sir?
Similarly, you should do for remaining also, negative sequence also.
Sir, if we take the VA2 in the same manner as previous case, the alpha and alpha square has been changed, sir.
Follow the phasor diagram, please. Alpha into VA2 means what now?
No, sir. What I'm saying is, in the
just
VA2,
answer to me. Just answer to me. Alpha into VA2 is what? It is shifted
Alpha
by an angle of 120 degree.
Okay. VB2
so it will superimpose on VB2. So VB2 is nothing but alpha into VA2.
Okay, sir. Okay.
Again, B2 multiplied with alpha, it will come C2.
Okay.
So VC2 equals to alpha into VB2.
Okay, sir. Okay.
VB2 is nothing but alpha into VA2. So it's alpha square into VA2.
Sir, okay, sir. What you are saying is right, sir. And my doubt, what I'm thinking is the VA2 will be as reference. I'm taking as a horizontal axis.
Okay.
Then the VB2 will be upward direction with 120 degrees, and VCT will be this like direction. What we say in left side direction, 120 degrees this place.
Okay.
The same manner has been come, sir. What we have discussed, the same has been come or not?
Same will come, obviously. Same will come.
So can you please explain in this page or any as references as horizontal as VAT?
Check this.
Okay, sir. Okay.
That you have to draw and you have to experience, Sir Ahmad.
Okay. Thank you, sir. Okay.
Have you attempted it by drawing the phasor diagram?
Yes, sir.
Have you attempted like this?
No, sir. I'm sorry. I didn't attempt due to the class.
You have to attempt it first. You have to attempt it and check it.
Yeah, class is going very fast. That's why I didn't attempt. Okay, sir. Okay. Thank you. Thank you.
Yeah, Ashish Raj.
Hello, sir.
Tell me, Ashish Raj.
Sir, actually, that classroom question, sir, question number 2.
Okay, what you have in that?
Sir, there is means there are 2 transformer. One's rating is 20 MV and second one is of 10 MV. Sir.
Okay.
So I have doubt that how they are connected, sir. Means this power should be the MVA rating should be same, sir. Means if they are connected.
MVA rating need not to be same. Voltage rating should be same.
Okay, sir.
Voltage rating we will
Yesterday-
follow in the synchronization. We don't follow MVA ratings, right?
Yesterday you mentioned that that rating should be same.
Voltage. We talked about only voltage, right, Ashish?
Okay, sir.
Okay.
Okay, sir. That yes, sir. Yes. Thank you. Sir, sir, hello. Sir, means
tell me, Ashish.
more, sir, how can we get more question on this topic, sir? Per unit, sir. Means
You-
there are only
You go through that Havari textbook, Professor Havari.
Okay, sir.
Just you download that copy from internet.
Okay, sir. Okay, sir.
Okay, so you can get number of questions in that.
Thank you, sir.
Okay.
Thank you, sir.
Vaishnavi.
Sir, in 53F, sir.
Tell me, Vaishnavi.
Sir, before page, sir. Before page.
Okay.
Sir, కేస్ 2 చెప్పారు కదా సార్, లోడ్ న్యూట్రల్ అన్గ్రౌండెడ్ అని.
Yeah.
అక్కడ కేసీఎల్ అప్లై చేశారు కదా సార్, అప్పుడు
Hmm.
న్యూట్రల్ కరెంట్ అనేది 0 కాదు కదా సార్.
ఎందుకనమ్మా?
సార్ అన్గ్రౌండెడ్ అయినప్పుడు
No, neutral current to grounded current అంతా వదిలేసేయండి. You forget about all those things. You have higher current going down.
ఎస్ సార్.
IB current going up.
ఎస్ సార్.
This is 0. Stand at this node. How many currents are entering?
ఓకే సార్. 3 కరెంట్స్ ఆర్ ఎంటరింగ్.
Sum of the 3 currents is 0.
ఓకే సార్. నేనంటే కన్ఫ్యూజ్ అయ్యాను సార్, అక్కడ న్యూట్రల్ అన్గ్రౌండెడ్ అట్లా అనేసరికి.
Okay.
సార్ ఇంకొకటి
Hmm.
21F సార్. 21F.
Okay.
సార్ ఇది సార్ ఇక్కడ ఫేజ్ షిఫ్ట్ ఆపరేటర్ తర్వాత కొన్ని ఫేజర్ డయాగ్రామ్స్ వేసి చెప్పారు కదా సార్, ఆల్ఫా మైనస్ ఆల్ఫా స్క్వేర్ ఫేజ్ డయాగ్రామ్. ఇక్కడ సార్ ఇక్కడ నేను వెక్టర్ సమ్ చేశాను సార్, కానీ నాకు 0 వస్తుంది సార్. ఎక్కడ తప్పు
ఎక్కడమ్మా?
చేస్తున్నాను?
Which value you are getting 0?
ఇక్కడ ఆల్ఫా మైనస్ ఆల్ఫా స్క్వేర్ మనము వెక్టర్ అడిషన్ చేసినప్పుడు రూట్ ఆఫ్ ఆల్ఫా.
This is alpha. Minus alpha square means what? You should reverse this alpha square.
నాకు ఇది ఫేజర్ డయాగ్రామ్ అర్థమైంది సార్. ఇక్కడ √3 యాంగిల్ 90 వచ్చేసి మీరు వెక్టర్ సమ్ చేయాలన్నారు కదా సార్. అది చేస్తుంటే నాకు 0 వస్తుంది సార్. 0 వస్తుంది సార్.
Magnitude.
ఎస్ సార్. ఎస్ సార్.
If you are confusing with that, you substitute alpha in rectangular form.
ఓకే. ఇట్లా ఓకే సార్, ఇట్లా అర్థమైంది సార్. కానీ అట్లా చేస్తే ఎందుకు అట్లా 0 వస్తుందో అర్థం కాదు.
You have to apply that what we call parallelogram principle to get this magnitude, right?
ఎస్ సార్. రూట్ ఆఫ్ ఆల్ఫా ప్లస్ ఆల్ఫా పవర్ 4 ప్లస్ 2 కాస్ ఆఫ్ 60 degrees కదా సార్ వచ్చేది.
Tell me again.
రూట్ ఆఫ్ ఆల్ఫా స్క్వేర్ ప్లస్ ఆల్ఫా పవర్ 4 ప్లస్
Alpha square.
ప్లస్ ఆల్ఫా పవర్ 4.
Okay. Alpha square plus alpha power 4 means alpha square plus
Alpha.
alpha. Okay.
Yes, sir.
Next.
ప్లస్ 2 times of cos
2 times of Cos?
60 degrees సార్. 60 degrees.
60 degree. Okay. Cos 60. 1/2.
1/2. ఎస్ సార్. దెన్ ఆల్ఫా స్క్వేర్ ప్లస్ ఆల్ఫా ప్లస్ 1 అంటే 0 కదా సార్. అప్పుడు
ఇప్పుడు ఒక మైనస్ ఏదో మిస్ అయినట్టున్నారు చూడండి ఒకసారి. మైనస్ ఆల్ఫా స్క్వేర్ కదా, ఇంకొక సెకండ్ ఫేజర్ మీకు.
మైనస్ ఆల్ఫా స్క్వేర్ ఉన్నా అది ఆల్ఫా పవర్ 4 అవుతుంది కదా సార్.
Minus alpha square. In your parallelogram principle, if one side is P, other side is Q.
ఎస్ సార్.
What is the diagonal? Root of?
రూట్ ఆఫ్ a స్క్వేర్ ప్లస్ b స్క్వేర్ ప్లస్ 2ab కాస్ ఆఫ్ యాంగిల్ బిట్వీన్ a అండ్ b.
Plus 2AB cos of angle between them. Na?
ఎస్ సార్.
What is it plus 2AB here? 2 into alpha into minus alpha square.
ఓకే సార్.
There you get one minus sign, right?
ఎస్ సార్. ఎస్ సార్. ఐ అండర్స్టాండ్.
Okay.
ఓకే సార్. మరి
By that you get the
ఇంకొకటి.
square root of minus 3.
ఎస్ సార్.
Square root of minus 3 is J root 3.
ఎస్ సార్ ఇప్పుడు మనం VA01 VA1 VA2 అవి ఉన్నాయి కదా సార్, అవి మనం సిమెట్రికల్ కాంపోనెంట్స్ ఆర్ సీక్వెన్స్ కాంపోనెంట్స్ అంటామా సార్ వాటిని?
Any name you can call. Either you can call symmetrical components or you can call sequence component.
ఒకవేళ ఫేస్ కాంపోనెంట్స్ అంటే ABC అని అంటాం
ABC.
కదా సార్?
Yes. ABC.
Yes sir. Okay sir. Understand sir.
Okay. Any other doubt you have, Vaishnavi?
No sir. Cleared sir.
Okay. Thank you. Jitendra.
Hello.
Tell me, Jitendra.
Sir, in the statement that you gave today, where you said that if any system consists of both positive and negative sequence, then it is definitely unbalanced.
Yes.
Sir, in the beginning only we discussed that if VA plus VB plus VC is equal to 0, in that system may be balanced or may not be balanced. So both possibilities can be there. So that system also has both positive and negative sequence, and yet we are saying that it can be or cannot be balanced.
No. If the system is consisting only positive sequence, it is balanced.
Yes, sir. That is, if only positive or only negative, then it is balanced. But if both are there, then it should be
unbalanced.
Like, sir, may be or may not be, no?
Why may not be?
Sir, because VA plus VB plus VC, that only example if we are taking.
That is 0. See, if VA plus VB plus VC equals 0, that does not mean that system is balanced, right?
So that does not mean system is unbalanced also, no sir? It is like
that does not mean system is unbalanced also. Means VA plus VB plus VC equals 0 is a necessary condition, but not sufficient to say system is balanced.
Yes, sir. That is not sufficient. So means it should not be the general statement, no sir? What you are saying that
statement. I said already, it should not be the general statement.
For that, if positive and negative sequence both are there in a system, then it is definitely unbalanced. It is
definitely unbalanced. Yes.
How it is definitely unbalanced, sir? That I'm
That's
not.
what I proved in this phasor diagram. This one positive sequence I have taken.
Sir,
negative sequence.
Sir, please just listen this. If let's say VA plus VB plus VC is equal to 0, you are taking that as an example, let's say. So it will have a positive also, it will have a negative also.
It may be, may not be.
Yes, sir. It may be or may not be. And it will have a positive also and negative also sequence.
Yes.
So it has a positive also and negative also, and it may be or may not be. So that means it can be balanced also, not at one point. It can be.
It can be balanced also, I said, right? It may or may not be balanced.
So sir, it has positive and negative, and yet it can be balanced. So the others
how you are missing that statement. If VA plus VB plus VC equals to 0, then system may or may not be balanced.
Yes, sir.
When it is balanced means if the system is consisting only positive sequence component or only negative sequence component, then automatically VA plus VB plus VC equals to 0, system is balanced.
Yes, sir.
If the system is consisting both positive and negative sequence component, even though you have VA plus VB plus VC equals to 0, system is unbalanced.
Okay. So, okay. But sir, this point is clear to me that it will be unbalanced. But sir, how?
How in the sense, positive and negative sequence components, if you have, you are getting resultant voltages in the manner of unbalanced only, right?
Sir, but for different values, like you have drawn this for one particular set, no?
You take any two phasor diagrams of positive and negative sequences.
They will never come balanced.
It will never come balanced.
Okay, sir.
You take any numbers you.
Okay, so that was my doubt. Thank you so much, sir.
Okay. Shivaram Krishna.
Hello, sir.
Tell me, Shivaram Krishna.
Sir, good evening, sir. Sir, page number 21, sir. 21. Sir, ఇప్పుడు ఇక్కడ left side.
Yeah, one minute, please. 1 minute. Yeah, dear Mr. Harshavardhan, measurements 3 hours in mornings are no problem. I said it's only for 1 or 2 days. We don't keep the classes morning 3 hours, evening 6 hours throughout a month. Only 1 or 2 days. How can't you adjust, Mr. Harshavardhan? We might be having an issue. Faculty issues will be there. Network issues will be there. Okay? Yeah. Tell me, Shivaram Krishna.
సార్ ఇవి ఇప్పుడు లెఫ్ట్ సైడ్ మనము ఇది అన్బ్యాలెన్స్డ్ సిస్టమ్ కదా సార్ విఏ విబి విసి ఇవి 3 మ్యాగ్నిట్యూడ్స్ వేరే ఉంటాయి అంతే కదా సార్
Maybe.
విఏ విబి విసి అయితే ఇప్పుడు ఇక్కడ దిక్కు మనం తీసుకొచ్చినప్పుడు 2 పాజిటివ్ నెగటివ్ గా రాసుకున్నాం సీక్వెన్స్ ఇక్కడ అప్పుడు విఏ1 విబి1 విసి1 3 మ్యాగ్నిట్యూడ్స్ ఈక్వల్ ఉంటాయి ఫేజ్ డిఫరెన్స్ 120 ఉంటుంది అంతే కదా సార్
VA1, VB1, VC1 magnitudes will be equal, phase shift will be 120 degree.
అయితే మనం జీరో సీక్వెన్స్ కాంపోనెంట్స్ ఎందుకు వచ్చినాయంటే ఇప్పుడు ఇట్లా తీసుకున్నాక ఇందులో మిగిలిపోయిన జీరో సీక్వెన్స్ గా రాసుకుంటాం
ఈ రెండు ఈ పాజిటివ్ అండ్ నెగటివ్ యాడ్ చేసిన తర్వాత
ఇంకా మిగిలిపోయిన
you
మ్యాగ్నిట్యూడ్స్ ని
still
zero sequence-
having some value in phase A voltage, that is VA0.
అయితే ఇక్కడ విఏ0 విబి0 విసి0 3 వాల్యూస్ ఈక్వల్ ఉంటాయా సార్ ఇవి పక్కా
Yes, yes, yes.
అయితే మనము ఇట్లా
Listen. Such that we are making the division.
సార్ నాట్ అండర్స్టాండ్ సార్
We are dividing this unbalanced phasors into set of balanced and co-phasal.
ఎస్ సార్
We are dividing in such a way that all the 3 zero sequence components are equal.
అయితే నాకు వచ్చిన డౌట్ ఏంటంటే ఇదే సార్ ఇట్లా డివైడ్ చేసినప్పుడు 3 ఈక్వల్ వస్తాయా రావా అని చెప్పి
We are forcing that condition, right?
ఓకే సార్
We are keeping that as a condition. Then only we are going for the positive sequence and negative sequence division.
దిస్ ఈ కోఫేజల్ సీక్వెన్స్ అనేది అన్బ్యాలెన్స్డ్ కదా సార్ ఇప్పుడు
Co-phasal sequence,
అన్బ్యాలెన్స్డ్ కదా సార్
I don't say it's unbalanced or balanced. We will say simply 3 phases are having equal voltages.
ఓకే సార్
That's it. Okay?
ఓకే సార్ థ్యాంక్ యూ సార్
Yeah. Yeah, sorry, Harshvardhan. I think I have misunderstood you. Sorry, Harshvardhan. Okay? You are very positive. Thank you. Sirisha. Please convey the message in a proper way, Harshvardhan. Sirisha. Sirisha, are you there? Do you have any doubt, Sirisha? Okay,
Hello,
fine.
good evening, sir.
Good evening, Sirisha. Tell me.
Sorry, sir, no doubt. I have cleared this now.
Yeah, okay.
Thank you, sir.
Is Tulasi.
Hello, sir.
Tell me, Tulasi.
Sir, in 63F, sir.
63.
Sir, 1 minute. సార్ మామూలుగా మనము S is equals to V into I conjugate రాస్తాం కదండి సార్
Yeah.
మరి ఇక్కడ 3 into S012 రాసినప్పుడు అక్కడ ట్రాన్స్పోజ్ ఉంది కదండి సార్ మనకి అప్పుడు ఎలా రాస్తున్నాం సార్ దాన్ని ఈక్వల్స్ టు S012 అని
What is SABC?
SABC is equals to VA conjugate into
VABC transpose into IABC conjugate.
yes sir.
But simply what you got here is 012. Yes or no?
Yes sir.
012. And here also you got 012.
Yes sir.
Then why can't I call this as S012 now?
Okay sir.
Okay?
Yes sir. Sir, in first day problem, sir, 37F, you gave one homework problem, sir.
Tell me.
Akkada magnitude.
Yeah, for those, 1 minute, Sirisha, I want to make some answer. See, for those homework problems, whoever is having doubts, or if you have solved already, just put it in Telegram. Put it in Telegram, and I will check the answers and I will confirm it. Okay? Tell me, Sirisha, what's your doubt now?
Sir. సార్ ఫస్ట్ డే హోంవర్క్ ప్రాబ్లమ్ సార్. ఫైండ్ ద జనరేటర్ ఇంపెడెన్స్ మాగ్నిట్యూడ్ ఇన్ పర్ యూనిట్ ఫార్మ్. అది నాకు అర్థం కాలేదు సార్. ఆ క్వశ్చన్ ఏం సాల్వ్ చేయాలి?
You have some resistance there.
ఎస్ సార్.
How much?
0.5
Ohms or per unit?
ohms only sir.
Ohms. What is the resistance? So reactance?
J1 sir.
J1. So you have impedance Z equals to 0.5 plus J1 ohm.
Yes sir.
And you calculate Z base. I think you have already done there.
4 sir.
4 ohms.
Yes.
Now what is Z in per unit? ZG by
Z by
0.5
Z.
plus J1 by 4.
Oh.
So I get point, I think 125 plus
Yes,
J 0.25.
25.
And you need only magnitude of this. Mod ZG per unit equals to square root of this number. 0.125 square
Plus
0.25 square.
oh, okay.
Okay?
Okay sir. I got it. Sir, another doubt sir. In 52F sir.
1 minute.
Okay.
For the telegram, please contact to my number 96184 61918. 96184 61918. Please contact to this telegram number. Okay, tell me, Sirisha.
Sir, in 52F sir.
52. Okay.
Sir, అక్కడ క్వశ్చన్ లో బ్యాలెన్స్డ్ సప్లై అని ఏమి ఇవ్వలేదు సార్ వాళ్ళు.
But still we have to consider it as balanced only.
Okay.
Supply generally it will be balanced. So actually it's a balanced system. It's a balanced system. But that C contact was not closed.
Not closed.
Okay.
ఇలా ఇచ్చినప్పుడు ఎలా అప్రోచ్ అవ్వాలి సార్? అంటే ఒకవేళ క్వశ్చన్ లో అన్ని కరెక్ట్ గా ఇచ్చినప్పుడు ఇంకా సేమ్ న్యూట్రల్ తీసుకొని మనం సాల్వ్ చేయాలా సార్ ప్రాబ్లమ్స్?
That's what I am saying you, Sirisha. There is a lack of clarity in the problem.
Okay sir.
Okay, but if it's a gate examination, they don't give with this lack of clarity. They will give that question very clear.
Okay.
They will mention this type of load. Is it delta or star grounded? How is the source? Is it isolated neutral, grounded neutral? Whole data they will give in the question.
Okay.
Okay.
Thank you sir.
Tulasi, are you there?
సార్ ఇన్సేపు నేనే సార్ డౌట్స్ అడిగింది.
Okay, fine.
సార్ ఇంకొక డౌట్ ఉంది సార్.
Tell me.
సార్ ఇప్పుడు అదే సార్ VA plus VB plus VC is equals to 0 అన్నప్పుడు ఫైనల్ కన్క్లూజన్ ఏం సార్? మనకి సిస్టమ్ బ్యాలెన్స్డ్ అనా అన్బ్యాలెన్స్డ్ అనా సార్?
May or may not be.
మే ఆర్ మే నాట్ బి. ఇప్పుడు బోత్ పాజిటివ్ సీక్వెన్స్ నెగటివ్ సీక్వెన్స్ ఉండి VA plus VB plus VC is equals to 0 అన్నప్పుడు
Unbalanced.
అన్బ్యాలెన్స్ కన్ఫర్మ్.
Already you are saying positive and negative are there.
Yes sir.
Then you don't no need to think about other condition.
Okay, thank you.
Okay. Charan Reddy, Sai Charan Reddy. Sai Charan Reddy. Tell me, Sai Charan. Sai Charan, please tell me your doubt.
సార్ మీరు ఒక దగ్గర అన్బ్యాలెన్స్డ్ లో మళ్ళీ టూ కండిషన్స్ ఉంటాయి. ఆ టూ కండిషన్స్ ఒకవేళ సాటిస్ఫై అయితే అన్బ్యాలెన్స్ అని చెప్పారు కదా సార్. అది ఇక్కడ సార్ ఒక ప్రాబ్లం లో.
ఏ ప్రాబ్లం లో? Tell me data of problem. I will open it.
సార్ దీనిలోనే అనుకుంటా సార్. ఫస్ట్ కేసు సెకండ్ కేసు.
Do you have that problem in front of you in your notes?
I did not remember that page number, sir.
Page number is not an issue. Do you have that problem right now in your notes?
Sir. Wait, sir. I'll see, sir. Sir, you carry on with another one, sir.
Okay. Pallavi.
56H, sir. Sir, little confusion is here. I1 plus I2 equals to IA, and you said that these two currents are divided, how they are in delta.
IA current is entering here.
Yes.
Two paths are there.
I1.
I1, I2, I assumed. I don't know those numbers.
Sir, they current divide into two parts.
Current dividing rule. Okay. Two branches are there. Two paths you have. Two currents I have taken.
Yeah, sir.
Such that sum of these two equals to IA. This I1 current is flowing in this branch, reaches to this node.
Yes.
There is a three paths are there. So another paths are there to this node, but one path is showing zero current.
Yes, means
And
there is
definitely I1 current should go in the other path.
Yes, sir.
Again, I reach it to this node. I1 is coming from this branch. I2 is coming from the other branch. Sum of the two, I1 plus I2 will go out from this line.
Okay, sir.
That is IA.
Okay, sir. Clear.
And obviously, IB equals to minus IA, right?
Yeah. Opposite.
Opposite.
Okay. Thank you, sir. Clear.
Okay.
Hello, sir.
Tell me, Saicharan.
Sir, in this insufficient data problem only, sir.
Okay.
This one only, if in a first case, sir, neutral is grounded.
First case. Okay.
In this case, you told something about even though two neutrals are grounded, also the system would be unbalanced.
Because one is open right here. C is open.
Okay, sir. We assumed C is open or
they have given in the question, right?
Okay, sir.
Contacting line C of the triple pole switch, contactor fails to connect.
Okay, sir. Okay, sir. Okay, sir.
Okay, Saicharan. Okay. Yogashri.
Sir.
Yogashri.
Sir, I'm audible to you.
Yeah. Tell me.
Sir, alpha power 1000 అనే ఒక దాంట్లో రాశారు కదా సార్, ఒక PDF గుర్తుపెట్టుకోలేదు. అది డివైడెడ్ బై 3 అని 3 ఫేస్ ద్వారా తీసుకుంటున్నారు.
Alpha cube equals to 1, right?
Alpha cube equal to 1.
So whatever the power they have given, you have to rewrite that power as a multiple of 3.
Sir, I can't understand, sir.
Okay. See this. Alpha power 1000 here.
Yes, sir.
Just follow this what I have written. Alpha power 1000. That I have rewritten as alpha power 999 plus 1.
So the process is I understood
just,
that, but why we
listen.
are doing the divided by 3.
Yogashri.
Okay.
Please follow this what I am saying first. 1000 I have written as 999 plus 1. Okay.
Okay, sir.
Alpha power A plus B is nothing but alpha power A into alpha power B.
Yes, sir.
So alpha power 999 into alpha power 1. Alpha power 999, I will rewrite it as alpha cube whole power 333.
Okay.
Alpha cube is 1. So this whole number is 1. Remaining value alpha. Okay, Yogeshri, understood this?
Yes, sir. In 70 alpha power 79 also it is divided by 2 also, no, sir. That's why I'm asking.
Alpha cube, if you capable to get this alpha cube power something, alpha cube you can replace with 1, right?
No, sir. I'm asking alpha power 79 is there, no, sir.
Okay.
79 is there, no, sir. In that 78 is divisible by 2, no, sir.
78 is divisible by 2. Okay.
Alpha square and power is can take, no, sir, 30.
Power, how much you can write? 39. What you simplify from that? Alpha square power 39 I have written.
Okay.
What you can simplify from that? So if you write that as a alpha cube power something, alpha cube you can replace with 1, na?
Okay. Sir, alpha cube is equal to 1 because of that we are taking like that.
We are writing
everything.
that in the manner of alpha cube.
Okay.
That's a simplification you are doing.
Okay, sir.
Okay.
Okay, sir.
So that's why any power number you have that you try to write as a multiple of 3.
Okay, sir.
For example, if you have alpha power 1005. Okay.
Yes, sir.
How much is this number? You can write, see, 1005 is divisible with 3 directly.
Yes, sir.
Yes, sir. No, 1005 by 3, how much?
335.
1005 by 3, 335.
35.
Means what you write? Alpha cube whole power 335.
Yes, sir.
Alpha cube is 1. So it is 1. Answer. Alpha power 1005 is 1.
Okay, sir.
Understanding?
Yes, sir. I understood.
Okay. Is there any doubt you have, Yudhishri?
Sir, ఒక క్వశ్చన్ లో మీరు ఓన్లీ పాజిటివ్ సీక్వెన్స్ కండిషన్ అండ్ ఓన్లీ నెగటివ్ సీక్వెన్స్ కండిషన్ బోత్ ఆర్ కరెక్ట్ అని చెప్పారు కదా సార్. ఆప్షన్ ఏ అని నేను మెన్షన్ చేశాను దాంట్లో. అంటే అది కరెక్ట్ ఇది కరెక్ట్ 2 కరెక్ట్ అయినప్పుడు ఏదైనా ఆప్షన్ ఇవ్వచ్చా సార్ దానికి ఆ ప్రాబ్లం కి?
అది if it is a multiple choice question, we have to choose only one option among AB.
Yes sir.
Listen, then by common sense we should go for positive sequence only.
Okay, sir.
Because positive sequence is the original phase sequence of the system generally.
Yes, sir.
That's why if the system is balanced, the original phase sequence will exist in the system. That's it.
నెగటివ్ కండిషన్ లో తీసుకుంటేనేమో నెగటివ్ వస్తుంది కాబట్టి
mathematically negative sequence, if it is having only negative sequence, then also I will say it's balanced mathematically.
Okay, sir.
Okay.
Okay, sir.
Any other doubt you have, Yudhishri?
సో ఇంతకు ముందుకు ఒక అమ్మాయి వైష్ణవి అని ఒక అమ్మాయి చెప్పింది కదా సార్ ఒక ప్రాబ్లమ్ యాంగిల్ రావట్లేదు అని చెప్పింది కదా సార్ 1 + ఆల్ఫా మైనస్ ఆల్ఫా స్క్వేర్. ఒకసారి అది కండిషన్ ఒకసారి ఎక్స్ప్లెయిన్ చేస్తారా సార్? నాకు అది అర్థం కాలేదు.
ఈ కండిషన్
ఎస్ సార్.
ఆల్ఫా మైనస్ ఆల్ఫా స్క్వేర్.
సార్ అది యాంగిల్ ఎస్ సార్ అది యాంగిల్ తీసుకున్నాం కదా సార్ అది ఎట్లా వచ్చింది ఒకసారి ఎక్స్ప్లెయిన్ చేస్తారా?
90 degree.
ఎస్ సార్.
రెక్టాంగులర్ ఫామ్ లో సబ్స్టిట్యూట్ చేయండి. ఆల్ఫా యు టేక్ ఇన్ రెక్టాంగులర్ ఫామ్. Alpha square also you take in rectangular form.
Okay, sir.
Then you will get obviously this complex number.
Okay, sir. I understood.
Getting me,
Yes. Yes, sir. I understood, sir.
Okay.
Yes, sir.
Else you follow the phasor diagram. That's your wish.
Okay, sir.
Okay. Any doubt? Any other doubt you have?
No, sir.
Okay. Thank you. Sai Praneeth.
Yes, sir. Page number 16, sir.
16. Okay.
Sir, here how to here at this time I got the last of power, sir. How these equations came, sir? Like VA equals to VA1 plus VA2 plus VA0. And
that's what the basic conversion we have written earlier, right?
Phase shift.
That we have taken from previous slides only.
Yes, sir. A boy stands on that.
That's okay. That's okay. See, VA, VB, VC, we are dividing into positive sequence, negative sequence, and zero sequence.
Okay, sir.
Such that VA is equals to VA1 plus VA2 plus VA0.
Positive sequence plus negative sequence plus zero sequence.
Phase A positive sequence plus phase A negative sequence plus phase A zero sequence. That summation is the phase A voltage.
That summation is a
phase A voltage.
Phase E voltage. Okay, sir.
Similarly, phase B positive sequence, phase B negative sequence, phase B zero sequence. That summation is a phase B voltage.
Phase B voltage.
Similarly, phase C also.
That this is the same thing you said there.
Same equations we copied there.
Okay, sir. And previously you said something about rectangle and something. No, sir, I didn't understand what it is meant by rectangle, sir.
No, rectangular form, alpha plus j beta, sorry, A plus JB form. Polar form and rectangular form, no?
అంటే 90 degrees ఎలా వచ్చింది అక్కడ?
See, this 90 degree we will get from this phasor diagram also, right?
Yes, sir. 120 minus 30, 120 minus 30, it becomes 90 degrees, sir.
90 degrees. Okay. What's your doubt further?
అంటే ఇక్కడ మరి మళ్ళీ రెక్టాంగిల్ అని దేనికన్నారు నాకు అర్థం కాదు.
Alpha equals to 180 angle 120 na?
Yes, sir.
Cos 120 plus j sin 120. So minus 1/2 plus j root 3 by 2.
Okay.
Alpha square 180 angle minus 120 degree. So it is minus 1/2 minus j root 3 by 2.
Alpha square. Okay, sir. It is negative unnadu kabatti minus j root 3
alpha minus alpha square is how much?
Minus
1/2 minus 1/2 will be cancelled out.
Okay.
Plus j root 3 by 2 minus of minus j root 3 by 2.
2j root 3 by 2 అంటే j root 3.
That's it.
Okay. ఇదా సార్? ఓకే సార్. అంటే ఇక్కడ రెక్టాంగిల్ అంటే రెండు కలపడమా సార్?
That's it. In that way also you can do the calculation I am saying. Either you follow phasor diagrams or you take the rectangular form values and you make that addition or subtraction what you want.
Okay, sir. Okay. And ఇంకొకటి ఇప్పుడు లైక్ ఇక్కడ ఇదే దాంట్లో ఆల్ఫా స్క్వేర్ మైనస్ ఆల్ఫా స్క్వేర్ సారీ సార్ ఇది కాదు, కింద ఆల్ఫా అనేది 1 ని లీడ్ చేస్తుంది కదా సార్ ఇక్కడ
బై 120 డిగ్రీ.
ఎందుకంటే ఇక్కడ మనం క్లాక్ వైస్
because alpha itself equals to 180 angle 120 degree.
120 degrees ఉన్నాయి సార్ మధ్యలో.
Alpha equals to 180 angle 120 degree, right?
sir.
So it has to be kept at an angle of 120 degree from 1 reference.
అంటే ఇప్పుడు ఆల్ఫా అనేదే కదా సార్ మనకి ఇక్కడ లీడ్ చేస్తుంది?
Yes.
Okay.
Alpha is leading with respect to 1 by 120 degree.
అండ్ మళ్ళీ ఆల్ఫా స్క్వేర్ కూడా ఆల్ఫాని లీడ్ చేస్తుంది సార్
120 degree.
ఓకే సార్. ఇప్పుడు ఇదంతా ఓన్లీ either క్లాక్ వైస్ తీసుకున్నా యాంటీ క్లాక్ వైస్ తీసుకున్నా ఇదే కండిషన్ సార్, లేకపోతే కండిషన్ మారుతుందా సార్?
These and all only for anti-clockwise we are discussing.
ఓకే సార్. ఓకే సార్.
Okay.
అంతే సార్. అంతే సార్. థ్యాంక్ యూ సార్.
Okay.
గుడ్ నైట్.
Good night. Mubin.
Hello, sir.
Tell me, Mubin.
Sir, we have one problem like the power supplied by the generator, and we are having RL load in series, and finally we have RL is a transmission line resistance and reactance. Finally, we have a load. Sir, in that you have asked to find reactive power delivered by generator in per unit form. So reactive power delivered by generator is equal to transformer reactance reactive power plus load reactive power. Both must be added and then it must be divided by base power. Now, sir, we have taken directly as generated equal to load. Why we have neglected transmission line?
You please read that problem. Do you have any transmission line in the problem?
Its question is not like transmission line. I'm just telling like that. A single phase generator.
The load is connected to generator. Whatever the generator reactive power delivery have, that itself is load reactive power, right?
I'm reading the question, sir. A single phase generator rated for 100 MVA 20 kV has the series impedance per phase as Z equal to 0.5 plus J1 ohms. It is delivering a load of 60 megawatts at 0.9 PF lag. Choose generator ratings as base values and find reactive power delivered by generator in per unit form. Sir, it means we have internal impedance of generator as 0.5 plus J1, sir. So should we consider that J1 observing reactive power?
Tell me.
Yeah, that one.
J1 is absorbing reactive power.
Yeah, that must be considered, sir.
This is one generator.
Yes, sir. And in series with R and X. It's
Physical generator. Physical.
Okay.
Not electrical circuit. Okay? It's a generator.
Yes.
This generator, you are drawing on the paper voltage source in series with its impedance.
Yes.
This is ZG. This is EG. Okay?
Yes.
Now tell me in a common sense, what is the reactive power delivered by generator? Where you find it?
Delivered by a
Generator. Delivered by generator.
It generated terminals.
Where? Terminals or source?
Terminals.
That's it. You yourself said the answer, right?
Yes, sir. But if in this figure it's clear, sir. But by reading question, it's not like that much clear, sir. I thought that.
No. What I am asking you, what is the reactive power delivered by the generator?
Yes.
Okay. Where you calculate? Is it a terminal or internal EMF?
No, a terminal only, sir.
What is accessible, which you can touch? Terminal or internal EMF?
Terminal only.
A terminal you have to find.
Yeah.
Not only here. What's your name? I have not seen your name. Mubin. Mubin.
Sir.
Not only here, anywhere, either in your synchronous machine, transformer, machine, wherever it is. If he is asking what is the real and reactive powers delivered by apparatus, means we have to find at the terminal of it.
Okay.
Because you no need to consider that internal things what we have. How much it is delivering, that you should know, right?
Yes, sir. Yes.
Okay?
Yes.
Yeah.
Sir, if we have transmission line, then we should consider.
How much is reactive power delivered by transmission line? I will ask you. Where you find at sending end side or receiving end side?
It's sending end side.
How much is a reactive power delivered by this transmission line?
Delivered by transmission and it ending, sir.
Yeah.
At ending.
At end. That's it. Delivered by line means at the end.
Yes, sir. Sir.
Delivered by generator means at the end of the generator.
Yes, sir. Yes. Sir, in the same question, if we ask the power delivered by generator, then reactance of transmission line is given. We have to calculate I and I square X.
You tell me, what is the load for this generator?
This is 60 megawatt.
Is it transmission line only or this load?
Load also, sir. Both.
What is the generator? What is the load on the generator? Is it transmission line plus load or only load?
Transmission line plus load.
So you have to calculate the total real and reactive power consumption by this load. That is the real and reactive power delivered by generator.
Sir, a small clarity I need, sir. Sir, the load power factor angle is given, sir. With that, we can find angle. And transmission line resistance and reactance is given. With that also, we can find angle. After adding these two reactances, we should add that angle also, sir. Or we should.
What is the basis of adding that angle?
Actually, I need to know per unit form.
One thing, Mubin.
Sir.
If you are adding something together,
sir,
either we have to satisfy KCL or KVL. Yes or no?
Yes, yes.
What you are applying there by adding the angle, KVL or KCL?
I'm adding impedance only, sir. Means Z transmission line plus Z load. But along with that angle.
Z line, Z load you have. Okay, that's good. That's good. You have load impedance here. You have the line impedance here.
Yes.
Can we add these two, Z line and Z load?
Yes, we can.
How? Why?
Series impedance.
What's the rule?
Yes.
This is having some value 10 at an angle 80 degree ohms. Load impedance is 200 at an angle plus 30 degree ohms.
Yes.
Can I add 80 degree, 30 degree together?
80, 30.
80 degree, 30 degree, can I add?
Sir,
that's not the rule to me, right?
Yes.
I have to add 10 at an angle 80 degree and 200 at an angle 30 degree.
Yes, yes.
I should not add angles together.
Yes.
Okay.
Sir, yes, sir. If we get after adding this, we get as 202 at an angle 60 like that, sir.
Okay. Okay.
So then what does that implies? It implies that power at that we have QG bus bar, sir. That bus bar. The voltage at that point and current through that line and the phase angle between that only, sir.
That's it.
Okay, sir.
You know, this is VS something. VS by Z line plus Z load will give some current.
Yes.
By using that current and voltage, you are capable to find this real and reactive powers.
Sir, that basic things only not clear, sir. Always I'll confuse, sir, on that things.
Okay.
That's why I'm clarifying. Thank you, sir.
No issue. No issue. If you have any silly doubt, you can ask me. One of the greatest advantage of online class is I don't know your face, and your face will not be known to the other people. Okay.
Yes.
So you can ask any silly doubt in these classes. No issue.
And not silly, sir, but that will haunt our mind all the time when we solve, sir.
No. Actually, doubt is a doubt. That's it. Either it is a small one or big one. Okay, Mubin, any more doubts you have, Mubin? Tell me.
No, sir. Thank you.
That's it?
Yes.
Yeah. Anil Kumar.
Sir.
Tell me, Anil Kumar.
Sir, phase shift operator, sir. Sir, phase shift operator, sir.
Okay, tell me, what's the doubt you have?
I did not get that point without changing the phasor magnitude, sir. Can you please explain?
Without changing phasor magnitude means, for example, if you have already existing voltage 10 volts.
Yes, sir.
You should not change the magnitude of the voltage. You have to shift that voltage by an angle of 120 degree.
Okay, sir. Already we have.
Listen. Why I have taken that condition as without changing magnitude is because magnitudes of A1, B1, C1 are equal, right?
Yes, sir. Magnitude.
I don't need to consider the magnitude change here. I have to consider only phase angle change.
Yes, sir. Okay.
Okay.
Yes, sir. Sir, sir, another doubt, sir. Next slide. That alpha square. So squaring, we have to multiply the angle, sir.
Alpha square in the sense magnitude square, angle will be multiplied by 2.
Sir, next slide, phasor diagram, sir, in 26.
Sir, in this, how we can conclude that angle 90 degrees, sir, with respect to lagging or leading, which terms are alpha or alpha square?
With respect to one is your reference, right?
Yes, sir.
With respect to this reference, alpha minus alpha square will make an angle of 90 degree.
Okay, sir. Okay. Yes, sir. Always we can take with respect to 1.
With respect to 1 as a reference, always.
Okay,
1 means 1 at an angle 0.
Okay, sir. Thank you, sir.
Okay, Anil Kumar?
Thank you, sir. Yes, sir.
Okay, okay. Karthik.
Hello, sir. Good evening, sir.
Tell me, Karthik.
Sir, మీరు CRP questions open చేయగలరా sir? PDF ఒకసారి.
Okay. What you have problem in that?
Sir, అంటే దాంట్లో క్వశ్చన్ సార్ సెకండ్ క్వశ్చన్ దాంట్లో
0.36 per unit.
Sir?
0.36 per unit.
0.36 per unit, sir.
Okay, tell me what's your doubt in that.
అది కాదు సార్, దాంట్లో ఓ జనరేటర్ ఇచ్చారు, 2 ట్రాన్స్ఫార్మర్స్ ఉన్నాయి సార్. ట్రాన్స్ఫార్మర్ సెకండ్ ట్రాన్స్ఫార్మర్ లోడ్ సైడ్ లోడ్ ఇచ్చారు సార్. ఎస్ సార్. సార్ దాంట్లో మామూలుగా వాల్యూ ఆఫ్ లోడ్ ఇన్ పర్ యూనిట్ ఫార్మ్ ఇన్ జనరేట్ సర్క్యూట్ అంటే ఏం చేయాలి సార్? అంటే generator base values ను common base values గా
First,
తీసుకుని
first you answer this one. You answer this one. If I say simply load is 0.72 per unit,
yes sir,
what you consider that? Is it power or impedance?
impedance sir.
Power.
Okay sir, okay sir.
Not mention anything. If the load is 1 per unit, I'll say you should say it's a power.
Okay sir, అదే కన్ఫ్యూజ్ అయ్యాను సార్ అంటే
Listen. Okay. So that 0.72 per unit power demanded by the load on the base of 10 MVA.
ఓకే సార్, అది అర్థమైంది సార్, ప్రాసెస్ మొత్తం అర్థమైంది సార్, అది ఒకటే కన్ఫ్యూజ్ అయ్యాను.
How much is that per unit power in the generator circuit?
Yes sir.
What is the generator circuit rating?
20 MVA 13.8 kilo ohm.
20 MVA. We no need to bother about voltage now because we are dealing with power.
Yes sir.
So 20 MVA is a rating of the generator. So now your new base will be 20 MVA.
Yes sir.
If you select new base as 20 MVA, that will be common at all places.
Yes sir.
Now old base is 10 MVA, new base is 20 MVA. Old power per unit is 0.72. You convert that into per unit power.
సార్ అది ఓకే సార్, అంటే 1.44 వస్తుంది సార్ ఆన్సర్, కాకపోతే 36 అని ఇచ్చేస్తారు ఆప్షన్ చేయండి.
You check once again. 0.72 into 10 is actual.
Yes sir, by 20.
How much?
Okay sir.
0.36.
0.36.
Do you have
Okay,
that
sir.
option?
No sir, 36 is sir.
Remaining options you read once. 36. Second option.
1.44.
1.44.
0.72.
0.72.
0.18.
0.18.
Yes sir.
How are these options? Remaining 3 options you look.
Points లో ఉన్నాయి సార్.
In a proper way, not in points. 0.72 into 2.
Yes sir, yes sir. 0.72 into 2. 0.72 by 4.
By 4.
0.72 into.
So the first option may not be 36, what I feel. It will be 0.36.
Okay sir, okay sir.
Okay?
Okay sir, I
Maybe
understood sir.
I thought it's a printing mistake in gate question.
Okay sir. Thank you sir, thank you sir.
Okay. Meena.
Hello, sir.
Tell me, Meena.
Sir, VA plus VB plus VC is equal to 0 అన్నప్పుడు సిస్టమ్ ఈస్ బ్యాలెన్స్డ్ అండ్ అన్బ్యాలెన్స్డ్ అంటే మాగ్నిట్యూడ్ అండ్ ఫేజ్ యాంగిల్ అనేది డిఫరెన్స్ ఉండొచ్చు అనే సార్.
Yes, magnitude difference may be there. Phase angle difference may also be there.
Okay sir, thank you sir.
Okay.
Sir, my doubt is clear, sir.
Okay. Vishwani.
Good evening, sir.
Good evening. One minute, please, Vishwani. Gurudatta?
Yes, sir.
Tell me, what's your doubt?
Yes, sir. I have a small doubt, sir. Sir, you said if a system consisting of positive or negative, then it is balanced. Then, sir, if a system consists of only 0 sequence, then it is balanced or unbalanced?
I can't make a comment on that. It's just like a single phase system.
Okay, sir. Then we
all
can
the 3
say...
phases are having same voltage, magnitude, same angle. No.
Okay, sir.
It's just like a single phase system.
Okay, sir. Then we can say as it is balanced or unbalanced.
It's not 3 phase system. What we say. Okay. I can't make that statement, but still I'm saying you, it's not a 3 phase system.
Okay, sir.
For example, I'll tell you. Yeah, so this voltage is 10 at an angle 0. This voltage is 10 at an angle 0. This voltage is 10 at an angle 0. This 1 ohm, 1 ohm, 1 ohm. Is it a 3-phase system or single phase system?
Single phase system, sir. As the phase difference is equal and
phase difference is not there.
Okay.
It's such type of system. Okay.
Okay, sir. Good. Thank you.
Shwani.
Yes, sir. Sir, Nina, manam Thevenin's impedance with respect to generator terminals all chestam kada sir. So akkada with respect to primary of transformer ante Z base values ela తీసుకోవాలి sir. Sir ఒకసారి generator with in series with transformer draw చేయాలి.
Generator in series with transformer. Okay.
Yes, sir. ఇక్కడ మనకి base values 11 kV 100 MVA వచ్చాయి.
Okay.
సో ఇక్కడ Z base మీద మనం with respect to generator అన్నారు కాబట్టి 11/√3/100/√3 అని తీసుకున్నాం.
100/3. That's it.
So with respect to primary of transformer ante appudu 11/100/√3.
Same.
But ఇక్కడ primary ane delta lo icharu sir.
Primary means what you are calculating. Is it winding impedance or at terminals? That's it.
Generate with respect to generator and transformer primary
Transformer terminals both are same.
Sir, ఇప్పుడు V base అనేది line to line voltage or just అది ఒక value లేకపోతే per phase?
That is your selection, right? Base values is our selection.
It doesn't represent line to line voltage or per phase.
We consider this as a line to line voltage base. We consider this as a 3-phase base. We consider. 11 kV you have taken as base. While you are writing that, I am choosing 11 kV as a base. You should tell what is at 11 kV, line to line or per base.
Anything considered.
We are taking that as line to line.
Per phase kuda teeskochu.
That's your wish. Per phase also you can take. Per phase you take, then multiply that with √3, you will get line to line voltage base again.
ఇక్కడ ఒక ప్రాబ్లమ్ లో 3 generators ఉన్న వాటి రేటింగ్స్ ఇచ్చారు.
Okay.
If in the same plant these generators are being replaced by a single equivalent generator అన్నారు sir. So ఆ equivalent generator అనేది ఎలా తీసుకోవాలి?
Rating of each generator is how much?
100 MVA 11 kV 0.15 per unit impedance. MVA 11 kV 0.15 per unit impedance.
So you are connecting 4 generators in parallel.
Three
generators in parallel of this type
are replaced by a single equivalent generator.
You are replacing this with a single generator. Okay. So without
usually they are not
base
connected in parallel, sir.
I connected in parallel, right?
Initially they are not connected in parallel. Just
That's
for
okay.
3 units.
That's okay. 3 units now connected in parallel. This is 0.15 per unit each generator reactance.
Yes, sir.
Now you assume this 100 MVA 11 kV itself has base values. So obviously generator 1, 2, 3 will have equal reactances 0.15 per unit. Okay, Vishwani?
ఇక్కడ అంటే ఇప్పుడు ఈక్వివలెంట్ లో 0.15 per unit ఉంటుందా by 3 అవుతుందా sir?
I have not completed the question. Listen. 0.15, 0.15, 0.15.
Yes,
now
sir.
to find out the Thevenin reactance, we should kill these sources.
Not Thevenin, sir.
Equivalent means Thevenin only, right?
Okay, sir.
You want to replace this 3 generators in parallel with 1 generator, right?
Yes, sir.
Then we have to draw equivalent circuit of this one, and we have to find out the equivalent reactance with respect to these terminals.
Okay, sir.
So by killing the sources, 0.15, 0.15, 0.15 will be in parallel. So it will come 0.05 per unit.
ఇప్పుడు ఇలా బేస్ వాల్యూస్ తీసుకున్నాం కదా సార్ ఇట్లా సో ఇది ప్యారలల్ లో కనెక్ట్ చేసినప్పుడు ఓకే సార్
So this will be again on the base of 100 MVA 11 kV only. It's 0.05 per unit you got, right?
Yes.
That is again on the base of 100 MVA, 11 kV.
300 MVA, 11 kV.
100 MVA. Because 0.15 per unit, 0.15, 0.15. This is on 100 MVA base, right?
Yes, sir.
0.15 per unit is on 100 MVA base.
Yes. సార్ ఇప్పుడు నార్మల్ గా 3 ఫేజ్ అని ఇచ్చారు అనుకోండి, దాన్ని ఎలా కన్సిడర్ డెల్టా ఆర్ స్టార్ కన్సిడర్ చేయమంటారు?
Mostly we will consider that as star only.
Thank you.
Okay.
Sir, one more doubt.
Tell me, Vishwan.
First day మీరు ఇది పర్ యూనిట్ డెల్టా టు స్టార్ కన్వర్ట్ చేసినప్పుడు ఇంపెడెన్స్ పర్ యూనిట్ చేంజ్ అవ్వదా అని చెప్తారు సార్. కాకపోతే ఒక కేసు తీసుకున్నారు మీరు, అది బై 3 అయింది అక్కడ.
అది పర్ ఫేజ్ డెల్టా.
అక్కడ అంటే ఇది క్లారిటీ ఉంది సార్, అంటే స్టార్ టు డెల్టా చేసిన డెల్టా టు స్టార్ చేస్తే పర్ యూనిట్ ఇంపెడెన్స్ చేంజ్ అవ్వదు.
ఫేజ్ ఏ, ఫేజ్ బి, ఫేజ్ సి ఉంటాయి కాబట్టి అలా కన్వర్ట్ చేస్తే మీకు చేంజ్ అవ్వదు వాల్యూ.
నాకు బై 3 అర్థం అవ్వలేదు సార్.
పర్ ఫేజ్ డెల్టా, do you know about per phase delta and three phase delta?
No, sir. Phase delta.
Per phase delta and three phase delta, do you know, Vishwani?
No, sir, I don't.
I have drawn the big diagram, right?
Yes, sir.
There I have explained phase A loop delta.
Phase A is in delta, B is in delta, C is in delta, but A, B, C combinedly are not in delta.
Not in delta.
Also clear. Yes, sir. But how by 3? I'm not okay.
If it is phase A delta, per phase delta, 0.2 per unit is each line reactance. You convert the delta to star, it will become by 3, right? Because Z base is not changing, na?
Okay. Yes, sir. Thank you, sir.
Okay. Next. Anybody? Siddharth.
Hello, sir.
Tell me, Siddharth.
Sir,
anybody have doubts? Please raise your hands.
In one
Siddharth,
assumption, you have taken load neutral ground is also grounded. So in that, how can you say that it is balanced?
He said in the problem, right? Balance.
So directly we taken the values, current values has directly.
He has given the current value 25 amperes.
Yes, sir. So that angle, how we have taken, sir? Like if it is.
We have taken phase A current as a reference.
Okay. Okay, sir. So it is balance. Then that's why we have taken balance angles, like 0 and minus 120. Okay,
0 and minus 120 according to voltage.
Okay, sir. Thank you.
Any other doubts? Please raise your hands. So can we leave for this day?
Hello, sir.
Who is this?
So Siddharth only, sir.
Siddharth. Tell me, Siddharth.
Sir, in this, if one current is not one current is 0, no, sir. So even though one current is 0, how can we say it is balanced?
Phase A is closed or not with ground?
Yes, sir. It is closed. So ground
And
is
that
acting
voltage
as
by
a path, sir.
impedance.
Ground is acting as other path, sir.
Ground will carry IA plus IB current.
Okay, sir. That because of that grounding only, it is balanced.
Balanced, exactly speaking. IA and IB currents are coming in that manner. Because IC is 0. You should not use a word of balance.
Okay. There is a path for that currents. IA and...
There is a path for IA plus IB.
Okay.
And both neutrals are grounded properly.
Okay,
so
sir.
phase A voltage will directly appear across this load. Phase B voltage directly appears across this load.
Okay, sir. Okay, sir. Thank you, sir. Okay.
Vaishnavi.
Sir, 26, sir. Page number 26, sir. సార్ ఇక్కడ నేను వెక్టర్ అడిషన్ చేస్తుంటే నాకు -2 యాంగిల్ 90 degrees వస్తుంది సార్. వెక్టర్ అడిషన్ చేస్తుంటే అప్పటి నుంచి ట్రై చేస్తున్నాను సార్.
Right, see, a square plus b square plus 2ab cos 60, right?
Yes sir, yes sir.
A square means alpha square.
Yes sir.
Plus b square means alpha power 4.
Yes sir.
Alpha power 4 is nothing but alpha.
Yes sir.
Alpha plus alpha square is -1.
Yes sir, yes sir.
Okay, plus 2a alpha b minus alpha square into cos 60.
Yes sir. అది కూడా అది -1 అయిపోతుంది కదా సార్. -1.
Cos 30, I think it is. Cos 60 or cos 30?
Cos 16 కదా సార్. ఆల్ఫాకి మైనస్ ఆల్ఫా స్క్వేర్ కి మధ్యన ఉండేది యాంగిల్.
That is 60, okay.
A కి B కి మధ్యన ఉండేది. Nice.
You check that parallelogram equation once again.
Yes sir, I checked it so many times sir. ఈ ఆల్ఫాకి మైనస్ ఆల్ఫా స్క్వేర్
30 degree. Cos 30 √3/2 square.
Sir, hello sir.
Tell me.
Sir, చెప్పండి. నెట్వర్క్ ఇష్యూ.
A square plus b square.
Yes sir. Plus 2ab cos of angle between A and B, sir.
Cos of angle between A and B.
Yes sir.
Alpha square minus alpha square alpha power 4 1. Then it will be alpha square plus alpha. Alpha square plus alpha is -1.
Yes sir, -1.
First two number summation -1. Next number
2 into alpha into minus
cancelled
alpha.
out. 2 will be cancelled out, and again you will get 1 there.
Yes sir, -1 will be.
-1. Check it once again. This is a parallelogram.
Yes.
A you want to find this value now. Okay. And you consider this whole angle, or we'll see what to consider. Can draw one vertical line here. Okay.
Yes sir.
Vertical line. Then this is a right angle triangle.
Yes sir.
And this one is again a right angle triangle.
Yes sir.
Okay.
Yes sir.
And you consider this angle as theta for time being. Theta.
Okay.
So this side, you know, B. And what will happen to this? This is O. You assume it is C.
Yes.
How much is that OC? You can say
OC equal to root of OB square plus
OC equals to how much you can get? B sin theta.
Sir, OC, it is hypotenuse, no, sir.
Hypotenuse. Take cos theta is what?
Yes, sir.
Cos theta is what?
OC,
Adjacent
sir.
side by hypotenuse.
Hypotenuse. Yes, sir. Yes.
So it is B cos theta equals to
B by OC.
B by OC.
OC.
Then what is OC? B by cos theta.
B.
B by
Yes,
cos
sir.
theta.
Yes, sir. Yes.
This is one thing. OC.
Yes, sir.
And you have to get this line. OC
Yes.
and this you assume D.
Yes.
That's
Sir,
CD.
అంటే మనకి డైరెక్ట్ ఫార్ములా తెలుసు కదా సార్, దాని ఫార్ములా రూట్ ఆఫ్ ఏ స్క్వేర్ ప్లస్ బి స్క్వేర్ ప్లస్ 2ab
Root of A square plus B square
ప్లస్ 2ab
2AB
cos of angle between A and B.
cos of angle between A and B.
A
So
and B.
whole angle you have to consider.
Yes, sir.
This total angle.
Yes. Sir, అదే కదా సార్, టోటల్ యాంగిలే కదా సార్
I
కన్సిడర్
don't
చేస్తాం.
think so. Is it total angle or only half? Once you confirm that equation, is it half or total angle?
Okay, sir.
You have that equation now?
Yes, sir. 1 second, sir. That is total angle only, sir.
Total angle. Okay.
Yes, sir.
Total angle is theta you take.
Yes, sir.
Okay. Now one is alpha, other one is minus alpha square.
Yes, sir.
Okay. See, we are missing very basic point. It's only magnitude, right?
Yes. Yes, sir.
It's only magnitude of the phasor. That
Yes,
we are
sir.
missing
Okay,
from
sir.
many times. Okay, fine.
Okay, sir. అంటే
Not
మళ్ళీ మీరు
substitute with
చెప్పినారు కదా
angles.
సార్, మైనస్ సైన్
Yeah.
తీసుకోవాలి.
By mistake, I have said in that manner. Only magnitude. Okay.
ఇప్పుడు వస్తుంది సార్. ఓకే సార్.
Nehali.
Hello, sir.
Tell me, Nehali.
Sir, in 20F.
Tell me.
Sir, that there we have completed 2 points, and the second point, even after doing this conversion, sir, will you please extend it once?
No, actually, phase A voltage was divided into VA1, VA2.
Yes, sir.
Phase A voltage was divided into VA1, VA2. But still, if there is some value left in the phase A,
okay,
then it is going to be taken as zero sequence component.
Sir, but what exactly means that left value means?
So that left value in the sense, first you see this. See, VA, VB, VC, unbalanced voltage you have now.
Yes, sir.
This you are converting into sum of balanced and zero sequence.
Yes, sir.
Okay?
Yes, sir.
Now, without this zero sequence component, I can't say that sum of these two equals to ABC voltages.
Okay, okay.
It may not be possible.
Okay, sir.
Okay? So, the resultant or residual quantity, what we have to add to the system of positive and negative sequences will be, to get this unbalanced voltages will be called as zero sequence.
Okay, sir.
Okay, any other doubts? So I think I can leave. Thank you.